Okay, look, hi again. We managed to have you here, I think, and everyone now can see you.
I don't hear you.
Organizing committee to have the conference. Here we are meeting about
so okay. I learned my lesson. I won't be screaming this time. Although I will not do that. So welcome, everybody. We're just about to start the final, but first we have a really important person who's going to talk with us today. The president of the European Physics Society. Luc Berger, I think he can listen to us fine, right?
Yes, I can hear you, I think.
Yes, oh, that's nice, man. So please, this is.
I do not hear you any longer now. I don't know why. First of all, I mean, do you hear me correctly? Because okay, this is not my case. So that's complete silence from my side. But anyway, maybe it's good. See? First of all, I would like, I mean, to thank you very much for the kind invitation proposed. So I am Luc Berger. I'm the president of the European Physical Society. And it happens that the European Physical Society has regularly supported for many years several similar events like the international physics Olympiads or international physicist tournament. I mean, on last Sunday, I had a similar role for delivering the prizes of the Planck's competition organized by the International Association of Students in Physics. So for me, it's a real pleasure, I mean, to be with you here and to give you my greetings. So as far as I heard, I mean, there will be the final competition right now, yes. And so I imagine that, I mean, only some teams have been selected, I don't know, from Brazil or dedicated countries, yes. So first, I would like to congratulate the finalists. I mean, this is a very nice achievement. As far as I can guess, the International Physicists Tournament aims at fostering the interactions of physics students from different countries over the world. And this is a way to increase the international collaborations. Here you have Brazil, Switzerland, and France. Thank you very much, Anastasia. I am very happy to see that we have a French team among the finalists. I don't know why, but perhaps if you hear my accent, and if you listen to my accent, you may guess easily. And this competition consists of solving certain physical problems. So it addresses master students, perhaps bachelor students. I am right? Okay. Good, thanks. And this the tournament this year included, I mean, the first ever hybrid conference for the ITP. Yes, so congratulations to the organizers too, because I mean, this was a challenge, I can imagine. Oh. Yes, good. Let me just briefly remind you what is the European Physical Society. The European Physical Society is an umbrella organization for 42 European countries. So that start from France, let's say, and then you go to Belarus, even Ukraine, and you know, I mean, the sad events that are happening in Ukraine, and from Greece to Finland. So we work together with the 42 member societies that includes the German Physical Society, the Institute of Physics in UK, and many others, and we prepare joint projects with them. We, of course, advocate physics and the role of physics in science, in academic institutions for sure, but also the impact of physics in the societal, economical, cultural, and social advancement in Europe and beyond in the world. So we have many actions at the European Commission. I mean, we lobby with them in order to improve education questions, I mean, the training of students, of course, and also how we can foster and help countries that belong to the eastern and southern parts of Europe. Typically, we have 18 divisions and groups, scientific divisions and groups. So, I mean, you know, I mean, that goes from laser physics to nuclear and particle physics, condensed matter physics, solar physics, and so on. We have also dedicated societal committees like the Physics for Education group, the Physics for Education division, excuse me, the Physics for Development group that aims at helping young researchers that work in low-income countries. We have the Equal Opportunities Committee that aims at reducing the gender gap in science and also at fostering better inclusion of physicists. And we have the Young Minds, I mean, the equivalent of you guys, I mean, in Europe, I mean, all the Young Minds community that are distributed through a pool of 45 sections throughout. So on the whole, we have in charge a little bit more than 130,000 physicists that share our goals and our activities. Of course, one of our main missions is to foster and to help the young generation of physicists. This year, in a couple of weeks, we will open the first EPS forum. I don't know if you have heard of it, but this will be the first time that we will bring all together PhD, postdoc students, even master students, who will have the opportunity to exchange with the most famous industrial partners in physics on different topics in physics. So this will be the day one. It will be on June 2 at Sorbonne University in Paris. And the day after, we will have a societal colloquium, societal conference, hosting a Nobel session with Barry Barish, John Kusterlitz, Serge Haroche, and also some parallel sessions discussed and shared by the most prominent scientists in Europe and even in the world. And besides, there will be some roundtable to think about how to improve the situation of young physicists, how to improve the activities of the learned societies, like the EPS, for instance. So you see a very dense meeting, and I am very happy to be at the origin of this event, and I hope that some of you will come in Paris. And if this is not the case, you are welcome to come probably to Germany in 2 years for the second edition of this meeting. Please be aware that we offer the lodging, I mean the accommodations, meals, to some tens of students, so you can benefit of that. Okay. Well, waiting for that, I am very happy that you organized such a nice event as the International Physicist Tournament. This is great. Bravo to the Swedes, Brazil, and French. You saw I didn't start with French. Eh? Okay. So I'm pretty sure that you will enjoy the competition. I'm pretty sure that also you will enjoy the prize. And if there is a nice event like a barbecue at the end of this event, please share it and be happy with that. So this is exactly the kind of initiative which the European Physical Society loves to support. And therefore, I'm glad and proud, I mean, to congratulate all the organizers, all the participants of this exceptional event, which the EPS will continue to support in the coming years. So thank you very much for your attention. Enjoy a happy final participation, and bravo in advance to the winners and to all others.
All right. Now I think we will move on to the captain's fights. Yeah.
Because they have the
With an echo.
First then, I'd like the chair members to introduce themselves once again.
Hi guys, I'm from the University of London in particle physics.
enjoy the play. And there's a no from the national program. No, bring it back. Hello, I'm Christoph Kozinski from the University of Warsaw. I'm a theoretical cosmologist and a deputy dean of the Faculty of Physics at the University of Warsaw. And I have to say that I consider myself a graduate of the International Physics Tournament because most that I learned about social dynamics in science comes from this event. And I'm not convincing that I learned a lot of physics. And I wish that's not only for myself today, but well, the competition is just a pretext to learn.
Hi, I'm David Cohen. I am an experimental quantum physicist, just finishing up at the Council Institute of Technology in Germany. I'm currently part of the Hexagon, where I've been president in the past. I hope this will be an excellent and just as good repeat as 2018, and if not better. So good luck to all the fighters. Maybe some vengeance coming into play.
Hello, I am Federico Serrano, Colombia. I am a PhD student in Washington State University. I am a astroparticle physicist, and I've been involved in IPT since 2015 when I participated in the national selection, and I lost. But it's okay. Now I'm doing it.
My name is Susanne. I do experimental science and catalysis at the Technical University of Denmark. And I'm looking forward to some fruitful and constructive discussions, please. So good luck to all the teams.
Hi everyone, I'm Anastasia. I also do remember for the final apparently, despite not sitting here, but I will as soon as possible. I'm Anastasia, I'm research fellow of University College London, IPT president, former participant and organizer. I very much hope to see a cool final because the previous selection and semi-final fights were extremely nice. I enjoyed it very much and it's great. Congratulations to all of you. Best of luck to the participants and do your best.
Hello everyone, my name is Fluctuation. I'm currently doing a PhD at the Technical University of Denmark on theoretical magnetism. I was also an IPT participant in the 2018 and 19 editions, and I really look forward to seeing your award today. Good luck everyone.
Hi, I'm Paweł Szybkowski, the team leader of Team Poland, and I'm really happy that despite the lack of sleep and the partying yesterday, you are all here to hear some physics. And I really hope and wish the final will show us really nice physics excitement that you have about it, and well, good luck.
Now, the chair of the final, Camila Diaz.
Hi everyone. Here we can continue with the introduction of the team. So we'll start over here with Team Brazil.
Good morning, everyone. We are Team Brazil, the quantum coaches. We are from Unicamp, the State University of Campinas. I am the captain, Leonardo. I am here with Lucas, Álvaro, João, Igor, and Gustavo, and we wish we'll have a great fight today.
Hello to all. I'm Mathieu Mauro, the team captain of France, and I'm going to present my team. So we have Antoine, Julien, Benjamin, Valentin, who's sick, but he's able to join us, so thank you very much, and Alexis. Also, Antoine has accompanied us.
So I'm Physicist. I am the captain of Team Switzerland, and this is Ryan, this is Pablo, this is Tobia, Yanis, and Elias. And I just want to say that we're really excited to be here. It was an amazing experience, and no matter what happens in the final, this was just amazing. Thank you, and good luck to everyone.
Okay, great introduction for the team. So thank you very much, everyone, our dear members, our team members, our spectators over there, and whoever is watching or from the live stream in YouTube. Hello. So to start our fight, we will begin with our captain's flag. Okay. So yeah. Good. So I will give the microphone to Alberto, who will explain us the fight while our team captains come here to the stage.
Everyone.
So, team captains, I will ask you to get what you want to see. You're gonna need help for this one. So, before we even show this, and take this. Oh, you wanted to write anything this time? I'm sorry. I mean, like, also some experiments. So, so each of these tables is for you. Right? So one table per team, and you're gonna be able to bring 2 team members for each of these 3 captain cards you're gonna have. You're gonna be able to change them in between them if you want. So then everyone can participate. So I mean, choose. Yeah, go and choose. So now that all the captains are here, I hope someone on the Hexagon has a timer ready. Perfect, thank you. So yeah, so that's how the 10 balloons, put as many as you can on the vertical wall in 2 minutes. So at the end of these 2 minutes, they have to stick to the wall with, of course, electrostatic force. You have to rub them on something, you have to blow them up, and no, don't blow them, I'm sorry, I mean, like, fill them with air. Yeah, no, but it's fine, like, it's now, it started. I don't know, the moment we showed the slide, it started, right? Guys, I don't know why, but I think my might be efficient.
Yes, true.
You have about 1 minute remaining. It doesn't. It seems like the participant's hair doesn't have enough electrons. 30 seconds. Oh, wow, we have one. Is that Team Switzerland or Team France? No, Team France, don't touch it. Be careful. 9, 8, 7, 6, 5, 4, 3, 2, 1. Oh! They fell. What does the jury say? Does it count or doesn't it count? That's actually true. It says within the 2 minutes, and the jury agrees that it counts. So we'll count that one.
We, the jury member, would like to demonstrate another way to win without using adhesives, which would consist basically of putting yourself against the wall, for example. You know? I mean, there's many ways you could win. But Alberto mentioned electrostatics, so they're like, oh, we're physicists, we love it. But sometimes it's just more simpler than that, right? Now we move on to the next question of the captain's fight. Well, and this round, so I believe we all agree that Switzerland got, 1 point. So Switzerland 1, France 0, Brazil 0. But of course, we're gonna have some more fun now. So let's go to the second. Yeah. So the question number 2 now. Let's see. You have 5 minutes. And please wait until I finish reading. Everybody's chill here. There's no rush, okay? You have 5 minutes to do the following problem. And please show on the screen. With A4 paper and tape, build the tallest paper tower. We're just gonna set this up real quick here. Give you some paper and everything. Yeah. Start strategizing. Huh? Okay. It's actually letter sized, not A4. But it's paper anyways, so I think it counts. No, wait. The timer hasn't started yet. We have to be fair. If you know what I mean, just watch the 2018 finals. You'll get just what I'm talking about. But, okay, well, put it back on. Okay, let's make it fair. Okay, everybody, start the same starting conditions. Come on. Let's just wait that. Just a little bit. Wait. Get ready. Get set. No, get set. Okay. Oh, no talking with the teams. All right. Wait. Oh, look at me. Team Brazil. The time will start now.
Also the other one. I didn't last one. Don't forget to let them stop.
Let them on?
Let them stop in 3 minutes. Because I want to let everyone participate.
Yeah, okay.
Now, now it's already started.
Oh, yeah, but on the first one, you said you told them to use electrostatics, like that was one. So it was like.
No, that was the point. The point was to misdirect them. And I did. Like, I understand what
Because this is how unfair stuff.
no, it's not. What are you talking about, man? It's not unfair. Like, they're building those are all three of them. Like those. Hey, let me measure. No, but then, no, but then, Mateus, I don't. I know what I'm doing. It wasn't unfair. I really think. Okay. 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 You finish this fight. Okay. No.
No, seriously. I'm being serious.
Half time. We have 2 minutes and a half left. One minute left.
Where's the measuring tape? Yeah, shut up.
20 seconds.
The measuring tape.
Alberto has it. I don't. Huh?
Alberto?
Yeah, Alberto has it. 7, 6, 5, 4, 3, 2, 1. Okay, stop it. Stop it. No more paper, no more scissors, no more tape.
Where's the tape? You have the tape? Or no? Oh, we have it. So, all right. So now we have a measuring tape as well. Let's see. All right. Well, you want to measure it?
Yeah.
Okay, so Mathieu will do the honors and measure.
Should we start here?
Yes, yes. This is Babel Tower, right? Like, a total of incredible. I'm just kidding. What would you say? An incredible amount of 23 centimeters. Now let's go to the second tower. This tower was inspired in ancient Greece, as you all know it. Wait, like, you want to climb? Yeah. Really? No, it's the height of the tower.
The height of the tower.
Yeah, the height of the tower.
Okay, you want to do this?
No, or you want to climb up?
It's fine. It should just be fair, right?
Let's see.
Put your cat down.
Let's see. Just to be fair, I think it's approximately 192. 1 meter 92. Yeah. Here we use metric. We don't do imperial. And now this sculpture I would like to call the paper man. Hold it down. Okay. It also serves to measure your height.
Yeah.
Can someone reach? Jesus Christ. What I can see here, it's 2 meters and 42 centimeters. Approximately. We're gonna take this statue to some countries. It's gonna be in Brazil for the next week or so, but then they'll visit France. Who knows? But you can buy the tickets. So for this round, I think Brazil gets the points, with France in second and Switzerland in third. But it was a beautiful effort, anyways.
Very valiant.
Very valiant. What? Sorry.
Come on, don't make the rules up now.
I think this is like. Yes, I think so. What? Because you got the first one. No,
Okay.
You make 2 points if you first, second, and since they tied, they say 0.
Yeah. Yeah.
Why France is one?
Because they were second. Makes sense. No, it's okay.
Oh, okay.
I would just like to clear with all the teams. Team from Brazil too, just to make sure how we're taking count on this. So for example, now the score is 2 for Brazil, 2 for Switzerland, and 1 for France. And Alberto, would you like to say something about the points, just to explain him?
Oh, so yeah, no, so we said that, like, if you're first, then you get 2 points. If you're second, you get 1, and third 0. But if you tie in second, then you get 0 points. If you tie in first, you get 1 point. Good.
Yeah, that was it. Just to make fair, everybody knows what's going on. There's no mysteries. Okay. Well, now we'll proceed to the third captain's fight, and now Alberto will do the honors.
So guys, let's start this fight, but let's first wait that you get all the boxes and open them.
Very heavy. If you tell me it's chocolate, I will hit you.
So actually, if you want to swap team members that help you, so to let participate all the people in the team, you can. Ok. Tu leur donnes un autre chacun.
Maintenant?
C'est-à-dire qu'il faut pas les casser. Donne-leur un autre chacun. So, what is Mathieu bringing to you guys? He has a gift. So, he's actually bringing each one of you an egg. And maybe some people that were here in 2018 might remember what's going to happen. So once everyone has the eggs, we can show them what they have to do. So for the material you can use is literally anything available with your hands. Anything. No, okay. So let's show this captain fight. Nastasia? So we were setting up for live stream, so the people on YouTube can see. Okay, so are we ready? Are we ready, guys? Woo! Oh, Tristan wants a timeout, apparently. Okay, so just stop the Steam member for this one. Tactical switch, yes, exactly. So you have 5 minutes to build. You can start now. So open the box and look inside. What you have to build is a protective layer for this for the shell of the egg, so that you can make it drop from the tallest level possible. So the way this will work is that you'll be able to choose the height from which you want to drop it, and then if it breaks, then you lose. If it doesn't break and someone beats you, you can one-up them. You only get one egg, only one chance. They can use anything they want that is available to them. So what have we got here? I see that all the teams seem very interested in the balloons. I will not disturb them for the next 4 minutes.
Yeah, I think he won, yeah? Yeah, I told him, yeah.
You guys have 3 minutes.
Hey, everything's good, man. I know, we all
Did I do better?
You
friends?
Yeah,
You don't
friends.
hate each other?
Hey,
Sorry, attention.
yeah, no problem.
You might want to feel me. 2.5 minutes left.
You have a nice camera there.
Oh yeah. What's the model?
It's
Wow. Sorry.
Oh yeah, we have the backup.
We have it. He has it. We have it.
We have the backup.
One minute left. Thirty seconds.
Seconds left. Six, 5, 4, 3, 2, 1. Time out. Stop building, and now will come. Okay. I wonder if they will break actually. So, Mathieu.
They're all gonna drop it from like all above.
I don't think it matters if we go outside actually. But let's say, okay, for the sake of it, let's give it a try and throw it from as high as you want, right? So I guess from the ceiling. Who wants to start? In case, so.
Okay, so maybe they all have to write it down.
Yeah, okay. All write down the height from which you want to throw it. Can we measure this?
I mean,
so we're having some trouble to measure the height of the ceiling. The meter is not long enough, apparently. It's not.
3 meters. 3 meters and 20.
3 meters and 20 is the ceiling. No, guys, don't kill yourselves. So,
Oh, Jesus Christ.
what is this construction that the Swiss have made? So they say it's a parachute.
262.
And that's at 262 meters.
This was like 320.
The French have it at 320. Yeah, guys.
We want to change our height, if possible.
Okay, so how much does Team Brazil have as height?
292 approximately, but
So 320 for Team France. So yeah, we're measuring from the position of the egg.
I mean, it's trivial.
That's 3 meters.
They have smaller balloons, so it's yeah, we have small. Yeah, I think it's pretty trivial that they are the highest. It's like 320, 305. No,
So,
it's more. They are higher because they have smaller balloons. Actually, our egg is in the top.
so there's some argument about the measurement technique. Apparently, you know, physicists, they're never gonna agree on anything. So, no, let's not throw it until it breaks. I don't think it's gonna break actually. So, let's go. 2, 1, drop. Ooh, actually no. I think eventually it's gonna break. Yeah. Let's keep it going. So now Team Switzerland needs to throw it at one time. Team Switzerland needs to throw. Oh wait. Let's. So in this case, it's a matter of resistance of the structure they made. Well, this doesn't look good. Okay, so let's throw it a second time altogether. Oh, it's inside. Okay, 3, 2, 1, drop. Oh! I think the next round for Team Brazil is out. The egg got dislodged from the protective shell, and it's in. Do you want to try another time? No, let's not do that. Let's try not to. Okay, so Brazil is 2 tries. Team France and Team Switzerland needs to do the second time. No, you don't have to repair it. Okay, then. Okay. He has to do it one more time. Well, okay. Oh, I think we have a tie here.
No, but ours is higher. Yeah, I guess. No. That's only because of the. We have eggs. Okay, as soon as this is a breakage of the rules, that we are changing the rules, I have one proposition. You might agree or not. The thing is that the eggs can break under the pressure. So for you, now the question is to put as many team members or people here at your design so that it does not break. Do you agree with that? So basically the thing is that you can stand, for example, on 10 eggs, yes? Like, just stand on them. But if you stand on one, it will break. So now the thing is to put as many team members as possible onto your design so that the egg won't break. But you have to agree for that, of course.
Okay, I like this idea. Actually, you take the other steam and you try to break it. Okay. Just by throwing it down. Oh, okay. Now Team France gets a try. Now wait, Team Switzerland. Oh, is there any way to tell actually?
I think it's broken. No way it's broken. No way it's broken. No way it's broken.
Yeah, I don't think it's broken. I'm sorry. Okay. Wow! No, we don't need a backup.
No, please.
We don't.
People in the chat ask.
But okay, if you don't
We don't
need it,
have one. We don't have one. No, but we don't need one. We choose on one. You said no. I mean, you want? You want? You want us to do one? But you want to do backup?
What? The backup, or are we good?
Whoa! So Team France managed to actually break Switzerland's.
Okay.
So what do we do? Anastasia, what do we do?
okay.
No?
If it's no time, we finish. Yeah.
What? There's no time. There's no time. No time. Okay, so we're gonna need to clean this up actually.
So it's a tie. What can we jump on?
No, actually, we can safely agree that Switzerland won. So, okay, this means 2 points for Switzerland, but actually puts them with 4 points for this captain fight, which means that they won the captain fight. But we have a tie for Brazil and France, with 2 points each. So actually now it's time to do a theoretical captain's fight. What? So, yeah. But before that, I think we should take a moment to clean up the mess.
Wow.
Oh my God, what the hell happened? Okay, maybe we shouldn't use the balloons. We should have told them not to use the balloons, I think. Can you give me some?
Sorry about that.
It's okay.
Study how fast, how further. Could we have done this with like fruits? Oh, it's gonna say.
No, it's not. Don't worry.
No worry.
We're gonna make it.
It's too crowded here in this.
Actually, we should have three points for no, because we didn't. Oh, really? Huh? Thank you so much. Yeah, I think it's a good idea.
There's lots of people. Like 10,000.
No, it's because they actually tied. We got points, so but then they won.
This is also cardiac. We were gonna present that.
They matched. They gave more tries of resistor, they matched.
It was fun.
1 point, so but then Switzerland got.
She's only between Brazil and France. Just to
T'as de l'œuf en
Everything is clean, like really fast.
We should also remove the table first.
Yes, please. Okay, so I'm going to ask everyone to leave the stage, but the team captains of France and Brazil. And bring something to calculate on. Okay, excellent. So we will break our tie with a theoretical captain's fight. So please, Anastasia, you will have 90 seconds to answer the following question. Most IPT participants made their way to Colombia by plane. Estimate the amount of fuel burned by the airplane taken by the participants from all countries. Account for round trips for all teams. Now, 45 seconds. Twenty seconds. 30 seconds, sorry. 15 seconds. 10, 9, 8, 7, right there. 5, 4, 3, 2, 1. Okay, stop for both teams. So can you write your answers on the board? Okay, so from France we have 10 to the 6 kilograms. Is that? Ah, okay, 3, 10 to the 5. Okay. Okay. And from Brazil we have 5 and 10 to the 9 kilograms. Okay, we can see the solution. Okay, so making the okay. We estimated with Google Maps that the total length of all flights from each national capital to be 262,692 kilometers, 14 capitals to Bogota, and back and 15 return flights to Bogota, Bucaramanga, with a 4.18 liter per kilometer average fuel rate. The total amount comes to 1.1 million liters and 0.88 million kilograms of fuel. Okay. Clearly, France has won the fight. No, don't leave. You too. And the team captain of Team Switzerland, please. Okay. So Team Switzerland won our main captain's fight. So you can choose in which order do you want to go. So first, second, third. Do you want to be the second? Okay. Then France, they want to be first, and you will be third. Okay, of course. So can you please go to the board and write in which order do you want to be? Oh yeah, sorry. Okay, thank you very much, guys. Can you please take a seat? So, in our first round, Switzerland will be the reporter, Brazil will be the opponent, and France will be the reviewer. They have to have their slides there. Yeah, but here, we're putting it out. Okay. So, as we already know which problems they are going to present, we're going to skip the all challenging part and accepting part. So, Team Switzerland, you have 5 minutes to prepare your presentation starting now.
Read the problem statements with it. Read the problem statements and show it. That would be nice. The problem statements, which one?
Well, I'm not sure. Like at almost every beginning of the presentation, they. Probably not. Because we're gonna report, but he's the main. I'm just Yanis Ulrich. Yanis Ulrich. And mine is Tobias Diamant. But he's the main reporter. He's gonna answer the questions. Thanks a lot.
Do you want to start now? Do you want to start now? Okay. Okay, so you want to start now? So now I give the mic to Janice and Tobias, and you can start.
Thank you. Okay, so hi everyone, my name is Yanis Ulrich.
My name is Tobias Fjellmann.
And we're going to be presenting problem number 17, resistor thermodynamics for Team Switzerland. So the problem asks us to analyze electrons in a resistor as a closed thermodynamic system at constant temperature. And we are then asked to use an electronic signal to determine some thermodynamic properties of the system. So the punchline is we managed to measure the Boltzmann constant with an impressive degree of precision using only the electrons in a resistor. And why this has anything to do with thermodynamic quantities and how we did it is what we're going to tell you now. So we're going to start off by talking about the theory behind all this. Then we'll discuss our experimental setup. And finally, we'll discuss our results. So at a microscopic scale, if you look at electrons in a conductor, because of their temperature, they tend to fluctuate a bit. We treat these electrons as a free electron gas. And actually, since every electron moving induces a current, that corresponds to a voltage, and there is some fluctuation in voltage on the conductor. So on average, by isotropy, this voltage will be 0, but we can analyze its variance, and maybe that quantifies some fluctuations for now. So to better understand what's going on, we kind of propose an analogy here. So if you analyze the random Brownian motion of a small particle in water, you can statistically deduce from that the viscosity of the water. And viscosity is really a dissipative phenomenon. So if you look, we can build an equivalence between a dissipative phenomenon and a fluctuative phenomenon. And it's this back and forth that's given by a theorem called the fluctuation dissipation theorem. So if we apply this to our case, we can see that electrons tend to fluctuate in the conductor. And we can ask ourselves what's the equivalent of the viscosity in this case. And this would be the resistance, which causes dissipation. So the question then is, could we build a link between the fluctuations of the electrons in the conductor and the dissipative phenomenon, which is resistance? And the answer is yes. And this is the formula that's actually proven in the article linked in the problem statement. And this is called the Johnson-Noyes formula. And the fluctuations are measured as a mean squared voltage in this case. And you can see that this is directly given as being proportional to temperature, resistance, but also the electrical bandwidth on which we're measuring. Boltzmann's constant also shows up. So if we plug some numbers into this formula, we might see that for a 10 kilo ohm resistor over 10 kilohertz bandwidth, we would have to measure really, really low voltages. And this is actually a big challenge. So we need to amplify the signal. So the basic setup of our experiment as a concept then would be that we have a resistor, we put it into an amplifier, the amplifier does something, and then we measure the output of the amplifier to try to quantify what happens in the system. So for this amplifier, we have a few requirements. If we look at the formula, the first thing we need that's obvious is a high gain, because we need to measure microvolts, we need to get somewhere to something usable. Next, we might see that since the voltage is proportional to bandwidth, we need a high bandwidth. This helps us out. And finally, since we're measuring very low quantities, we might want to have low amplifier noise so that the amplifier doesn't produce much more voltage than our resistor is. So we took all of these constraints and we decided to build our own amplifier, and we managed to do it for less than $100. This is the circuit we used. We decided to power it using two 9-volt batteries because that reduced noise by a factor of 10. We got this from an article online, and it's easily decomposable in 3 stages. So we successively amplify the signal even more over 3 amplification stages like so. So now that we have our amplifier, we need to understand what it really does. So for this, we kind of test it with an analysis device. And to do this, we just impose a sine wave at the input, and we assume an affine model where the input voltage is multiplied by some gain at that frequency, but there's also an added amplifier noise. So we test this for many, many different frequencies, and we also include the resistor we're testing here for some more complicated technical reasons we could go into later. So if we take this model here and we suppose that we've measured this function g, then we can look at the mean squared values and we see they evolve like this because the noise voltage is supposed independent of the input voltage. And we can also measure this noise by just using a 0 input voltage and then measure what comes out of our amplifier. So we obtain the following Bode diagrams, which just show the gain as a function of frequency. And we see it is relevant to include the resistor because it does change. And now that we have this formula, we can ask ourselves what actually happens to our Johnson noise formula. So this is the Johnson noise formula, if you recall, and this is what our amplifier does. So now we're just going to use this formula here, and we're going to plug it as the input voltage, and we're going to look what happens. So basically what we need to do is, since the gain is frequency dependent, we need to just integrate over all frequencies to properly implement the effect. So this is what we do here. We have an output voltage, which is noise voltage plus what the amplifier really amplifies. And practically everything drops out of the integral except for the gain squared. And we call this integral of all frequencies of the gain squared our function f of r. So from all of this, what we get is we get an effective version of the formula, which is actually measurable. So we write it right here. We simply define a new mean squared voltage as being the output voltage, but without the noise voltage. And we can say that theoretically this should be equal to 4 kBt times the resistance times our function f of r.
Now I'm going to take over, and basically I'm going to talk to you about how we did our measurements. So we use the setup on this diagram here, or on this picture here, which is in which we put our resistor in a temperature regulated system so that we can vary temperature. And basically we have an oven here and the wire, which we can fill with liquid nitrogen to regulate the temperature. We measure, as explained by Yannis, our Johnson noise thanks to our amplifier and a voltmeter. And since this is a really sensitive measurement, we actually also made sure that the whole system was electrically isolated, not to get any disturbance in our measurements, and also turned off the oven each time we wanted to take measurements, because that also affected them. So, wait, I'm having, okay, well, so for our measurements, basically, we have two free parameters in our formula which we want to check dependencies for. We have temperature here, and then this factor here, which is resistance times f of r. And we did this with different values of these parameters. So basically, we took 3 temperature values: room temperature, then about 200 Kelvin, and 430. And then we also took different resistances between 10 and 62 kilo ohms, and took the associated values of the factor that is here. So by doing this, we can actually plot the values and fit them for linear dependence. So basically for the law we just showed you. And this results in the plots we have on these 2 slides. As we can see, we truly see a good linear fitting. This is reflected both by just the fact that the points are on the curves, and as well by the R squared factors, which are really close to 1. Basically, we also included here the errors, not in the error bars because they were really small, so we just put the maximal errors here for you to check. And so now this proves the linearity of the formula, so basically the whole formula, and we now want to use it to solve the problem statement and determine which quantities we can measure. So I don't need, okay. So basically we have one equation and 5 quantities, so we need to measure 4 of them to then determine the last one. As you can see, we can measure both, we can measure all of these quantities, so temperature, resistance, and then the KB constant. And we can it's important to notice that we can measure all of these 3 quantities with the same precision. What we choose to do to test our model, to test our precision, is to measure KB, as we have a reference value for it. But it's really important to remember that we could have measured T and R with the same precision. So now, to measure KB, what we did is we took the points which I already showed you. We took some additional measurements, and with all of these points, we plotted them against the expected value, or rather, we plotted them, and we again fitted this line, which gives as a slope 4 times KB. As you can see, the value we get is extremely close to that of reference. It's about less than 1 per 1,000 away from the actual value. And we also have really, really good statistical significance, as the error is really, really small.
So now we're going to get into our conclusion. We started by presenting fluctuation dissipation analogy to better understand the phenomena, give you some intuition behind it. Then we talked to you about how we implemented our homemade amplifier and how we basically took the measurements, trying to get through the fact that it was a sensitive one and we had to deal with a lot of parameters to take really good measurements. And at the end, we introduced the thermodynamic quantities which we can measure, which are temperature, resistance, as well as the KB constant, which appears a lot in thermodynamics and statistical physics, and actually determine the precision to which we could determine these quantities. We got a result which was, to us, really impressive. And basically now, so we're done. I would like to thank you for your attention. I basically saw the time. I was like, I have to make it a little longer, but I didn't.
Thank you very much for the both of you for that wonderful presentation. And now we will go for the clarifying questions from the opponents. So, Team Brazil.
Really nice presentation, guys. Congratulations. I would like to start by asking, what is your effective gain on your circuit?
Could you clarify what you mean with effective gain?
Like you had an amplifier, right?
Yes.
What was your measured gain on it?
So this is actually the plot that shows the gain as a function of frequency, and it varies.
Okay, so what was the order of the signal that you actually measured? Order of magnitude,
at
sorry.
the output of the amplifier, you mean?
Yeah.
Millivolts.
Millivolts, great.
To sub-millivolt range.
I think slide 18, please. Could you say what is the most important thing that you consider for your error there?
So we have horizontal error, which is basically just measurement error of temperature or resistance. And on the vertical error, we observed on our multimeter the variance of our measurement, and we used this as an estimate of the error. So what you would see here is a 95% confidence interval.
Oh, great. Okay. I think slides, can you keep passing? No, passing forward. Yeah, slowly. Okay. And yeah, this is one point. No, the next one. Yeah. You only measure the Boltzmann constant, right?
So practically at the end, we verified this formula and we got a KB out of it. What we really measured is the voltage squared.
Yeah, you only can like measure one at a time, right?
Yeah.
Okay.
It's one equation.
And next one. There's the error. Yeah, okay. Thank you.
Okay, thank you for the questions. So now the opponent has 3 minutes to prepare.
no, it's going to be.
Okay, please silence. So now the opponent will make his presentation.
Good morning, everyone. I'm Leonardo Falabella, and I present the opponent presentation for problem 17, Resistor Thermodynamics. I'd like to start by congratulating the Swiss team for presenting us a very nice presentation. They really showed us with a great experimental setup how they actually measured the Boltzmann constant with an impressive precision. And so I'd like to start by pointing out some positive points on their presentation. First, they did a nice overview of literature. They present a nice knowledge of the theory of the phenomena and how they understand this. Another positive point is the random motion analogy with the Brownian motion, which is a great analogy that helps us how to understand the phenomena of thermal noise. They did a really robust experimental setup with adequate amplifiers and filters, which is not so simple to do. You have to really take care of other sources of noises on this kind of setup. So this was impressive. And they explored how they would calculate multiple thermodynamic constants. They said about the Boltzmann constant, the temperature, as well as the resistivity of the resistor. Now, some points that like they did a really good presentation, so I have to be a little maybe pet peeve on some negative points that it might improve their presentation. One of them is that they did not take care of other noises, or at least they didn't cite it on their presentation. I'd like to see how they treated like pink noise and white noise, which is really common on electrical circuits. Another negative point that might be improved is that they did not explain how the measurements were really thermal noise, and these 2 points are kind of similar, because it's really hard to tell if what you are really measuring is the thermal noise or just another source of noise in the system, because it is really small. And they actually only measured Boltzmann constant. They said how they would measure temperature and in resistivity. I would like to see that as well. It will be one more confirmation that they really nice experiment. But overall, it was a really great presentation. I think that they completely solved the problem statement. So on the point of discussion, I would like to see how their understanding and how their setup could extend to other parts of the phenomena and explore more of the limits of the model maybe. So starting, is knowing the origin of noise relevant to our measurement, and how do you correlate these two things? If you think that knowing about the origin of the noise is really important, we think that the origin of this noise is really important, and we'd like to discuss a little bit that. Another point is, how could you isolate your noise from external interference and internal noises? This comes back to my point that I already cited about other noises, other noise sources on the circuit. And now, exploring more of the limits of the model and the phenomena. Is it possible to measure Johnson noises without a resistance, which is really interesting for me at least? I'd like to discuss what they think about this. More like going on superconductor side. And the last point, are there any thermodynamics constants that you cannot measure, and why? And if they could explore maybe other constants on their experimental setup. But overall, again, it was a really great presentation. I tried to explore like the limits of the model and of their experimental setup to see what we can discuss. So maybe if you could share your screen, it would be really good. Thank you.
Yeah, we'll give you some time to set that up.
Oh,
No big
thanks.
deal? Okay.
Maybe we can start.
Sí.
Okay, so just to start with from ground up, what do you think about what is the origin of the thermal noise? Could you say a little bit about that?
So when you mean the origin of the thermal noise, you mean a physical intuition or?
Yeah, like where is this noise coming from?
Okay, so for me, the noise is simply coming from the thermal properties of the electrons. So by equipartition, or maybe even simpler concepts, you might say that temperature corresponds to kinetic energy in some way. And this means there's some electron movement. And this electron movement is what I consider we measure here due to temperature.
Oh yeah, we clearly agree on that. And one of the points that is really hard experimentally on this problem is to actually measure and know that you are actually measuring the thermal noise because it is so tiny. Could you explain how you are sure that you're actually measuring thermal noise and not other sources of noises?
Okay, so I think maybe here it's useful to clarify what other sources of noise there could be. You cited, for example, pink noise, so it's 1/f noise. Indeed, all of these sources of noise are a problem. So we also have external electromagnetic radiation coming in. I think those are the main ones. So external noise from radios, etc., and pink noise. Pink noise is a noise that happens for lower frequencies, which means what we did was actually filter out the lower frequencies of our spectrum. We had a low-pass filter, a high-pass filter, sorry, around 5 kilohertz, which tried to exclude that. For the electromagnetic radiation, this is a hard one to quantify. I agree with that, and we put it in a Faraday cage and noticed huge improvements. And at the end of the day, we assume that the electromagnetic radiation is relatively constant over time, so we put this in the amplifier noise. But in fact, this is an interesting point of discussion because we noticed that when our measurements were not done on the same day, there were ever so slight differences. Okay. So when we do these things, we try to do them quickly and we try to do them even at night so that there's not too much activity.
Yeah, that's a great point because we are dealing with very sensitive signals, right? So you're extremely right on that. Now, try to explore more of the limits of this phenomena. What do you think? Do you think that we could measure the thermal noise, this Johnson noise, without a resistance on a superconductor, for example?
This is a good question. So if you think about a superconductor, you would imagine it like electrons moving relatively freely around in it. And this means you would absolutely have a kind of current. There would be a current fluctuation. But because resistance could be considered close to zero, you would not have a voltage. So it would be a different type of measurement.
Yeah, I agree. But do you think that you could measure it somehow? And how would you do that?
Yeah, so you would have to change the setup of this amplifier to become a current amplifier. Because right now we can only amplify voltages effectively, I would say. I would consider it measurable, but I would expect it also to be very weak. So this might be another obstacle. I would not be able to estimate the order of magnitude, but I think it's very small.
Yeah, I totally agree with you. The way that I think we should move is by using the current to measure it. So I think we are on the same page here. And like, what do you think about the metallicity of the resistor? Do you think that what would happen if we were measuring the thermal noise, for example, for a semi-metal?
For a semiconductor, you mean?
Yeah.
Yeah. Okay. I think this is an interesting question. So to a first approximation, obviously the electrons do more or less the same thing. They fluctuate in it, but they have maybe some preferential places where they want to stay, some voltages they induce. To first approximation, I would imagine that we would measure a Johnson noise also on a diode, for example. But since the resistance works in a very special way in a diode, this voltage might change also in accordingly to these curves.
Okay, and what do you think about other external parameters like temperature on this case?
For the diode specifically, or?
No, semi-metals, semiconductors.
They're obviously very temperature dependent because that's the main way they work, right? So obviously they would be affected by temperature because there would be more electrons moving to a conducting band in them. So they would probably evolve from a more maybe capacitive behavior to a more resistive behavior when you increase temperature.
Yeah, I think we agree on that as well.
Okay.
Thank you very much for both of you. So now we move to the clarifying questions from the reviewer.
Thank you very much. I have a few questions. First of all, did you use any kind of wires in your setup? And if so, which wires did you use to connect the resistors with the amplifier, for example?
Okay, so basically, because of our experimental setup, we obviously needed a wire between the resistor and the amplifier. Inside the Faraday cage, we used standard copper wire.
Standard copper wire. Okay.
Outside of the Faraday cage, we used BNC cables, basically, to eliminate noise.
Okay, thank you. And can you tell us how you made sure that the regulation of the temperature, how did you regulate the temperature? So you used liquid nitrogen? Did you have some thermometers or things like that?
We had a platinum temperature sensor, and we basically simply had a PID controller on the system, which had with the oven and the liquid nitrogen, we were able to regulate to within 1 degree or maximum 2 degrees of precision.
No, it's my time to ask questions. Thank you. I have another question. Were you able to measure the electromagnetic field inside the Faraday cage?
We did not quantify this. We just put it into the amplifier noise.
Okay, thank you.
Can you just show us the experimental setup, please? Just for us to see it. Yeah, okay. Okay.
Please, could you go back to slide 17? I'm not very sure to understand the x-axis.
Oh, so basically these points are just the measurement points we made in some abstract parameter space. So you have temperature, and on the x-axis you have our resistance times our F function. The problem is we can't vary resistance and F independently, so we put them as one.
Thank you very much. Thank you.
As quick as possible, here you go.
Good. Et tu parles aussi des apports théoriques, enfin tu l'évoques, je pense, à un moment. Tu dis c'est un TP.
C'est clair pour le Zoulou ou pas?
Le pointeur marche pas. Non, c'est bon, ça marche.
You good?
Okay, so I think it's time. I'm Benjamin, and I will be reviewing for Team France. So I think we would all benefit from reading once again the statement of the problem. Thermal electrons in a resistor can be treated as closed thermodynamic systems, where the electrons are interacting with the rest of the conductor held at a finite constant temperature. create an experiment which allows you to investigate the thermodynamic properties of such a system using an electronic signal. Which thermodynamic quantities can you measure? So I'll start with the strong points of the reporter. We made a really good experiment. So we had good reminders of statistical physics, a really good introduction about fluctuation, dissipation, theorem. So it was a really nice insight. Your homemade setup was quite well isolated, in fact. And there is an apparent high precision of your results. Nevertheless, I think there are some big weak points of your presentation. Because you did not define properly the system, and I think that it's something really important in the problem statement. You did not mention parasitic noise in the presentation, and no order of magnitude about the noise, so I think it's something really important when you have such a precision. And no real physical insights about the Johnson-Nyquist formula, and I think that, in fact, you did not answer the question of the problem. Because the Boltzmann constant is a thermodynamical constant, but that's not a thermodynamical property of the system, such as its temperature, its entropy, or never, I don't know, but not the Boltzmann constant. About the opponent, I'm glad that you highlighted that the Boltzmann constant was the only thing that he measured, and you underline the difficulty of being sure that what we're measuring is only thermal noise and no other noise without order of magnitudes. Nevertheless, you say that the problem was solved, and I do not agree. Because the problem is not about thermodynamical constant, but thermodynamical properties of the system. Because knowing the Boltzmann constant does not give us any additional information about your specific resistor. That's just a tool. So here are my discussion points. So first, I think that defining the system and focusing on the thermodynamic properties that you measure may be something really interesting, because I think that your setup was great. So in fact, I think that we could all discuss about the way you could use it to answer precisely to the problem statement. So yeah, the thermodynamic properties of such a system, and also about uncertainties. I think that it's really important that we discuss things like electromagnetic noise, parasitic capacitance, control of temperature, and order of magnitudes to be sure that your amazing precision of 10 to the minus 5 is really what it is, and that there are not other noises.
Thank you, Benjamin. Your presentation is over. I will give the mic to the opponent.
Okay, so maybe I like to ask, to start by asking the opponent whether he thinks that the problem was solved or not, and maybe if you have any idea of, with the setups that they used, how they could measure some thermodynamic properties of the system.
Yeah, I actually cited on my presentation that they only measured the Boltzmann constant, and that even I asked about on the discussion how he could measure other thermodynamic properties. They said about measuring temperature and the resistivity of the resistor, and I really would look like to have seen this measurement. Maybe most importantly because of the precision that they get on their experiments.
Okay, maybe do you have any idea of thermodynamic properties that they could have measured with the experiment?
Yeah, of course. One of the thermodynamic properties that I think is really interesting that we can get with this kind of setup is a measurement of the absolute zero temperature. Yeah, I think this is one of the most impressive ones.
Okay, maybe the reporter, what do you think about whether you solved the problem or not, and what you can do with your setup?
So, to answer this question, you reported back to the problem statement. You did not really talk about the article linked in it. I think it's a very important aspect of it, because the article specifically is a proof, a theoretical one, of the Johnson-Noise formula. And in this sense, we consider that we solved the problem absolutely, because we investigated the fluctuation, dissipation physics that the question for us was getting at by linking this article. And we measured this with great precision, and we also did not only measure, in a sense, KB, but we implemented a setup capable of measuring all the thermodynamic quantities.
Okay, but what are these quantities? Can you tell us, please?
KB, is a constant, and
Yeah, a
T and
constant, but-
R
but
are the
things
parameters.
that are specific to the resistor and not universal physics constants.
T and R.
Okay. Maybe maybe I also like to ask, what do you think is kind of the theoretical value that you add to the article? Because you use the Johnson-Nyquist formula, so you deduce properties from this formula, but maybe it would have been interesting to add maybe some other theory to measure other properties.
Okay.
Do you have any idea about that?
If you guys would like it, we could definitely look at theoretical proofs of the equation. We have that, but I think what we truly add is the analogy. The analogy is our own work, and we consider it to explain the phenomenon in an interesting way.
Okay, and he raised the same point as I did, that it's really hard to be sure that you are really measuring the thermal noise here. What do you have to say about like the point that he raised about electromagnetic fields inside your box?
Maybe we can move on to maybe uncertainties. So can you tell us if you have taken into account parasitic capacitance? Do you have any order of magnitude, electromagnetic noise or things like that? And explain to the jury that you're certain that with your order of magnitude, you know that it does not perturbate your experiment and your result.
Okay. So parasitic capacitance is a good one, because if you look at our setup here, I mentioned we actually directly measured with the resistor under test our system. And we actually used the entire cabling setup that was in the end used. And the reason is parasitic capacitance. Because if you look at what the resistor does with the capacity, this actually builds a low-pass filter. And the problem is that changes the gain curve for different values of resistance. So this is what we were getting at with this plot. So we consider that we took into account a good number of parasitic capacitances, yes.
Okay, I understand your answer. And maybe just to focus back on the problem statement, we can talk a little bit about the system. So you talk about the temperature, but what the temperature of what system? The resistors, the electron gas?
Okay, very good question. So I would actually like to answer this by elaborating a bit more, if I may, on thermal capacities and conduction between the lattice and the electrons. Because,
okay, shortly, please.
Yes, shortly. Because the interesting part is we're actually not able to distinguish the electron temperature from the lattice temperature. Because if you look at this curve, within about 6 picoseconds, the temperature of the lattice, the spins and the electrons in a common iron, here it's nickel, but it's the same thing in iron, they tend to the same point. So we cannot investigate differences between these things. So
okay, maybe the opponent would like to add something about that.
Yeah, can you repeat the question?
Okay, so in fact, it talked about the temperature, the temperatures that you could measure, but I wonder what about like which system? Which system? The electron, the resistor, both of them?
Yeah, I think this really the same thing. The electron, the temperature of the electron, I think it's similar to the temperature of the resistor. So.
Okay, so we'll give. Maybe I have a question from Team Brazil.
So I would not expect there to be an issue with low temperatures, because putting amplifiers to low temperatures is a well-known method of improving their performance. High temperature, I mean, other than the obvious limits, no.
And this is for your. Oh, sorry.
Works even less well over temperature. The higher we go, the less well it works. More noise.
Okay, this is for the experimental measurements, right? But what about the formula? What do you think about extreme limits on temperature?
Okay.
The theoretical model.
So this model has been verified to very low temperatures, and in fact, if you go to millikelvin range or very high frequencies, you need a quantum correction for it, because there's an equipartition application in it and you require Fermi gases, etc. at low temperatures.
Yeah, do you think the equipartition principle holds at these low temperatures?
Not in the classical form. You need to implement energy using the Fermi-Dirac statistic. With that, I would say it works, and it's been experimentally verified.
Okay, I think we have a question first from Team Switzerland and then from Team France. Okay, but I think it would have been great to have order of magnitudes. Okay, from Team France.
Step by step, maybe, because for the parasitic for the parasitic capacitances, we considered them, so we implemented them in the solution, and yes, I would consider them definitely irrelevant because we considered everything even in the picofarad range, and everything beyond that would have filtered our system somewhere in the higher megahertz range, so it's perfectly irrelevant. Next part of the question. Next part of the question. I don't remember. But this is the frequencies we used. What do you mean? I don't get the question. Yeah, they're well-known values. Picofarads, the order of magnitude, but...
Okay, in the last 10 seconds, maybe from Brazil.
Okay.
Can I still answer?
10 seconds, quick.
Okay, with this setup, no, in theory, you would have probably some current fluctuations which we could measure.
Okay, thank you very much. So now we have the concluding remarks by our reporter. So please.
Okay, so to conclude, we presented an analogy for the formula we used, which we thought clarified the situation. We then built an experimental setup to measure the equation. I would like to thank the opponent for the fruitful discussion. I think there's even some subjects which we couldn't touch on, which would have been very, very nice. Thank you for the reviewer also. Maybe we disagree on some points, whether we solved the question, for example, but I think all in all, we did touch some very interesting subjects and also some very recent research, so I'd like to thank both of you.
We will continue with the questions, so I'll ask the opponent and the reporter to stand there and please share the mic. So who has a question first?
Okay, thank you. Very elegant solution. Maybe if I start with what seems to have been bothering a lot of the teams, which was the noise. Can possibly, trying to find a way to phrase this question, maybe to the opponent and the reviewer, in what way could you perfectly eliminate the noise from the amplifier setup? Do you have any proposals in mind for that?
Yeah, I think one of the simplest way is what they actually used, the bandwidth filter, but I think it's really hard to completely erase the noise from the amplifier.
Yeah, I think that we could add a lot of things, such as limiting the wire by connecting directly the components, and maybe a Faraday cage to protect from electromagnetic noise from the Earth's magnetic field.
So no one considered using two amplifiers and cross-correlating them? Okay, fair enough, fair enough. I have a lot more questions, but I'll try to pass them on to someone else.
Yeah, so a question about the experiment. What is the effective volume of the cooling chamber? Do you keep the amplifier in the cooling chamber, or do you have wires going out towards the amplifier?
The amplifier is outside the cooling chamber, and the volume of the cooling chamber I do not exactly know. I would estimate to something like a few liters.
So one end of the wire connected to the resistor is held at the temperature of the resistor, and the other is at room temperature, right?
Yes, there is basically this entire part is at the temperature of the chamber, and the other part.
So there's a strong gradient of temperature in the wire.
Yes, you would expect some kind of Seebeck effect, if that's what you're getting at, and we eliminate constant voltage.
Excellent. Okay, and if I may, just short one. Yeah. So this is a system in equilibrium. So you could define some sort of equation of state, I guess. And if you did that, and if you took it out of equilibrium, you could measure some other thermodynamic quantities, like changes in entropy, for example. Did you try to maybe do something in this effort?
We only did constant temperature measurements, but about the entropy is difficult because it's often an indirect measurement, right? You need a model of energy, and then only then can you do something. Also, heat capacities are difficult because they're not the ones of the electrons.
Okay, thank you.
So, theorist question phrased in two equivalent ways. First, for the last 2 years, the Boltzmann constant has been known exactly without any error. So I'm not actually sure what you mean by measuring the Boltzmann constant. Then during the discussion, you said that for thermodynamic quantities, your setup actually can measure temperature. So it looks like you are able to measure temperature in two different ways, one using the sensor, one using your Johnson noise thermometer. So that's my line of attack. I would be happy if you tell me that this is not just a Johnson noise thermometer that you built to measure the temperature of the resistor, and I would be very happy with reflections about that from the opponent and the reviewer.
So effectively, our setup could have been used as a Johnson noise thermometer, but we decided to use it to verify a value of the Boltzmann constant to show precision. As to whether this setup really distinguishes itself from a Johnson noise thermometer, I think that's difficult to say. I think it works very well as one, and I wouldn't distinguish it from one.
Yeah, I think it's the same thing as a Johnson thermometer. Is that another question? And I don't think it's like that.
I just wanted to give you the opportunity to speak about that.
Okay. Yeah, I think it's the same thing.
Well, I don't have much to add, but I think it's interesting to point out that Johnson-Nyquist noise appeared at the same time as the Brownian motion theory. It came from like the same thing. And Jean Perrin, a French scientist, actually used it to calculate the Avogadro constant. So yeah, I think it's a nice thing to calculate the Boltzmann constant too with that.
I have a question just for the reporter. You mentioned that at low temperature, you have to include in the model some quantum effects in Fermi gas. But I wonder at high temperature when the model breaks.
So as you saw, we went to about 430 Kelvin, and everything seemed all right experimentally. Beyond that, you have a lot of materials that you use that start melting, like solder, etc. So actually, as long as the metal really behaves as a solid and there's no phase transition, I would not expect a change in behavior.
I have a quick question for the opponent. So you brought up superconductors, which I found very interesting, and semiconductors. What is the resistance in a superconductor?
It's almost zero.
Almost zero?
Yeah, like experimentally?
It's zero.
Okay, sorry.
I have a question to the reporter. Can you click to the slide where you have this choice between you can either, this one, and while clicking on it, can you clarify for me how did you measure the gain curve? It was measured experimentally. Did I get it correctly?
Yes, absolutely. Yeah.
I didn't. Okay. I'm still looking at the slide. Okay, explain. You've been measuring what and what did you calculate?
So what we do is we have a system, a function generator that inputs a sine wave at a known amplitude. and then we look at what comes out. And to first approximation without distortion, it's another sine wave amplified by some factor plus noise. So we just, for every frequency, and this takes hours, this is a really long measurement. So for every frequency,
How many
we have
frequencies you did?
As an amount, we did, I think, 2,000 or 3,000 different frequencies for one curve.
To the reviewer and then to the opponent, do you, following this discussion, do you believe the reporter team measured with the stated precision? And if not, then why not?
Well, I think that they did not, because they were not able to give us. I mean, maybe they did, but if they don't have the order of magnitudes of the different phenomena that produce noise, then I can just trust them. I would have liked to see the order of magnitudes of the phenomenon. So I think that they maybe did, but they were unable to prove it.
Total effective noise of our system is equivalent to a 250 ohm resistor at the input. And we actually measured like 50,000 ohm about. So that's an order of magnitude of the noise.
Yeah, by precision, you mean the error that they get?
Yeah, the error on Boltzmann's constant that they quote.
Yeah, for me it's really precise, but again, I come back to the point that I don't know if all the noise they are measuring are really from thermal, and I'm not really sure if this uncertainty is really accurate. Maybe I think I would push it a little bit up.
Thank you.
Okay, so I'm almost convinced that you measured the thermal noise. The only thing that I lacked is that the thermal noise has a flat band. So basically, no matter what frequency, you should have like the same v squared. So do you have such a result to really make me certain that what you measure is a thermal noise?
Okay, so let me put it maybe this way. We, in our theoretical formula, supposed this. If you just go back a few more afterwards, basically the integral. We supposed this, and this is the formula we verified. So if there was a change in this behavior for the domain that we investigated, we would have expected a change in behavior. Like say if it dropped off at 100 kilohertz, we would have expected a change in behavior. We would have seen something else to us. We don't have further investigation on this.
Okay, and the question to the reviewer and the opponent, what could they do? Like, which graph should they show to me so that I'm certain? If you know what I'm talking about, yes, so that the band has to be flat, what should they show me to make me certain that the band is flat?
Yeah, I think on the x-axis of frequency, and the y-axis, I'd like to see the noise, so that they measured if it is flat.
Yeah, in fact, they should measure the noise and make the Fourier transform of the noise, and we should see like a constant function for the range of frequencies.
Okay, thanks.
I don't see any other jury questions, so thank you very much. Any other one? Okay, I will give the jury members their time to decide their marks, but we won't show them. So just write them, and you will give them to me later. Yes, the suspense.
Is it? Uh-oh, that's okay.
Okay. Okay, the jury. Are you ready?
We're not showing all rounds.
More or less. But you're ready. Yes, yeah. So as I told you, we won't show the grades today because it's the final. So we will leave that suspense for later. But I'll ask the jury members to give comments and remarks without disclosing their grades, please.
So I wanted to ask very quickly before questions, and did you use a dynamic spectrum analyzer to ever check what your noises were to tackle them? I'm just curious. Powerful tool. Feedback for the reviewer, probably. First of all, I really liked it, and I thought that you did it almost like exactly as I wished for it. A point for the opponent is why did you mention superconductors, and if they have no resistance? I was a bit unsure about that, unless, I mean, I do know that you can measure the Boltzmann constant from a superconducting via the superconducting gap, but I'm not sure if that was really part of the problem statement, because it's not the signal that it asks for.
But I think you can actually measure thermal noise from a superconductor.
How?
Using the what we said on the discussion, you have to actually measure current instead of voltage.
Okay.
So I would like to start with my remarks for the reporters team. I think that this was a situation like my mother asked me to go shopping and bring her potatoes, and I'm back with ice cream. Much nicer in the short run. So I very much like the solution. I have doubts that it answered the precise formulation of the problem. And if your understanding of the problem is so narrow, I think that you should have thought about other possibilities of the meaning of the task that is defined in the problem. I also have a little remark to the opponent team. I think that was almost ideal, except for the fact that you reiterated one issue, so the control of the electromagnetic radiation losses that was previously explained by the reporter. And for the, yes. And right, so this was for the reviewer. And one thing that I also didn't like, I'm sorry, I have to look up my notes, is that there was a quote, lack of explanation of the Johnson-Nyquist formula, so and the physical meaning thereof. So I'm afraid that this is a generic complaint. So when you don't have something to say during review, you say, show me more physics. So this is somehow void. I mean, it might lead to an interesting discussion, but generally it doesn't. So that is my issue. For the opponent, I think that you were a little bit too soft about the exact formulation of the problem. If you, of course, it is very difficult to press that some part of the problem wasn't addressed because it doesn't lead to an interesting conversation, but it wasn't sufficiently stressed, in my opinion. And I have to say that the discussion about experimental errors was interesting and enlightening, and it taught me a little bit more about the system that it's used in the presentation. So I'm greatly impressed, but with all the reservations that I've raised.
I agree with Christoph and also with David. I will just say something additional to the reporter. It is very important to recognize mistakes when they are very valid, and the opposition and also the reviewer brought into the discussion some of good points about how the problem was not solved. And during the debate, it was very hard for me to see that the reporter was giving up with this part of the problem. They were very stubborn about their solution, and that's it. That's my only comment about.
think I generally agree with everything that has been said, except for I think I was probably on the lower end with the reviewer grade, because I felt that there was parts of the presentation that maybe, like for example, with the Faraday cage, they did actually include one, which was then brought up again as the reviewer as a suggestion for how to improve it. Yeah, I think that there's maybe some things that were missed, unfortunately, but I think for the opponent and the reporter, I agree with everything that has been said. Yay.
I would also comment on the reviewers that you actually weren't quite attentive and careful about what's been in the report or what's been in the discussion. It's about the cage. Also, I noticed the point when you actually ignored the point raised by the opponent and started another conversation. It didn't look nice. Just try to be, as a moderator, actually kind of host on the stage, and you should take care of that everything like is heard and addressed and reiterated and like somehow converged to some logical ending. It's not kind of the job you did. And the reporter, you could do better if you been like more deeper into analysis, but it was actually, I understand, a difficult problem to oppose. So don't be super disappointed of yourself. Thank you.
I have little to add overall because I generally agree, but I would like to congratulate the reporting team on a very, very nice presentation. I'm not an experimentalist myself, but I felt it was really easy to follow what you had done.
Okay, to the reporter, I have no idea why did you choose the problem that you didn't solve. And this is actually the thing that I like about the review, and I didn't like about the opponent team. So the thing is that finally you said, sorry guys, you didn't solve the problem. And that was cool. And even not putting that on the discussion because, well, it's better to just discuss about what they really did was a very great job. Really, I missed it along the whole tournament to just say, sorry guys, you didn't do the problem. And you as the opponent have to do that, okay? Like it's your responsibility, and this is what I liked, mainly. Yeah, so I think that's all.
Okay, I just want to state I don't agree with Pavel completely. I agree with Krzysztof. Your mother sends you for potato, you bring back ice cream, but I would say in this case it's potato ice cream. I believe there is a solution to this problem hidden somewhere in there, but it's not been stated clearly in the presentation. I would have liked to see more of a discussion of what the thermodynamical properties really are, and if they cannot be measured, then fine, then they cannot be measured. But this is something you should probably state more clearly. And this is what I didn't like about the opposition, because we were kind of stuck on technical details more than formulation of the problem. And what I did appreciate about the reviewer, because it was the first thing he brought up in the end.
Okay, I think that we are done with the remarks from our jury. So we have finished the first round of the fight. Excellent to everyone. So we will have a little break through the door glasses back there. There is some food, so you can go and take it.
no una sola vez, puede haber sido una procedencia. ¿Sí? Lo que pasa es que el problema está pensando en por ejemplo, el artículo por ahí, ya lo estoy mirando mientras tanto, que ellos miden la temperatura del agua. Ajá, entonces, esa temperatura constante es la constante de uso. Lo utilizan para medir la temperatura. Pero para eso sería tendría que tener un cómputo electrónico de la resistencia y aumentar el número de electrones. O sea, tenerlo como una carga, ¿sí? Pues cargarlo como un condensador. Si hubiera podido usar un condensador con un eléctrico medio. Un condensador con una resistencia pero los falsos no es que o sea, las políticas o sea, claro, son un libro de ellos dijeron que instalar la potencial generado por el diferente pero es una pregunta de no sabe. Dicen que no. Que de pantalla agachada. Estoy buscando uno no sabe efectivamente qué tan se controla también la temperatura. Hay muchas cosas.
Ese problema está muy abierto, sí.
No sé si es abierto, porque realmente es una técnica conocida.
¿Ah, sí? ¿Hablando del paper?
Sí, no sacando un paper, pero sí, el amplificador sí es conocido en el sentido de que se sabe que tiene que medir ocasional, o sea, tienen cuántos artículos, inclusive páginas web donde muestran el montaje.
Eso es muy teórico, ya me di cuenta. O sea, en el amplificador junto con temperaturas y
yo aprendí eso cuando era chiquito, o sea, eso pero no contigo, o sea, pero sí el ruido es uniforme en frecuencia que depende del ancho de banda. ¿Sí? ¿Aló? William, ¿qué tal? Los amplificar se puede aumentar. Muchísimas gracias. Muchas gracias. Listo. Listo. O sea, eso yo lo pago, ¿no? No vayas a traerlo. Eso, muy bien. Listo. Oye, un abrazo. Muchísimas gracias. Chao. Sí, muy
So can we go back to our seats to continue the fight? Sit back, thank you. You won't disclose that. I can show you, but you cannot disclose that. Yeah, as you told me. Yeah, just wait. You broke it? Uh-huh. Anastasia has just left. Where's Team France?
Are you putting them on IPT Connect as we go along? Yeah, that way I can see.
Hide IPT Connect? Because they are already there, right?
Pues que no sé si haya alguna pero es que si suéltalo para tocaría
So, Team Switzerland, ready? You all there? You.
que taparse. Yo no traje nada.
So, Team Brazil, you ready? Please sit down.
What?
Please sit down. Sit down. Like sit. Team France, we are ready? Okay, good. Do you remember all of them here? Okay. So I'm gonna ask for silence back there. Thanks. Okay, I think we can continue with our second round. In this round, Brazil will be the reporter, France the opponent, and Switzerland the reviewer. So, as we already know which problems they are presenting, Brazil will present the problem number 1, physics of math. So, yeah, you can come. You have 5 minutes to prepare.
Señor, sí, señor. No, yo no sé, yo no sé,
¿Y de dónde la dejaron? ¿Pero será esta? Sí, creo que esta es de mate. Esta es de mate.
It should be.
Está rota. Está rayada.
Oh, yeah, it's here.
Tú la encontraste y estaba limpia, ¿verdad?
No, estaba así rota. Now it's
The internet is not working, so they can't join the Zoom call. That's what's happening. No, you have to accept them.
Would you like to start right away? No.
So the transition is okay. You can try to show the screen.
Okay.
I think we need the. No. These are. I think these are technical. Yeah. Or simply they could also see on you.
Good.
Show me what you're showing. Well, what you did that for last.
You know, the agua es un tema. Lista para hacer una mano. Pero el freestyle dice es buena.
¿Quieres agua para la agua?
No, quiero una tapa. Digamos, piensa decirle. Pero no, esa está llena. Está llena.
Not yet.
Seríamos famosos.
You can start.
Hello everyone, my name is Gustavo and I'm representing problem number 1, Physics of Math. So first, the problem statement. It's not working. The screen sharing. Yeah, we want a technical timeout. Okay. So let's try again. My name is Gustavo Frois, and I'll be presenting problem number 1, Physics of Math. So first, the problem statement. Build a device, no calculators and computers, please, that can be used to compute some famous mathematical constants in the most physically ingenious way. Optimize the accuracy of your device, and note there are, in addition to, for instance, pi and e, many other interesting constants, such as Aperri's constants and or Feigenbaum's constants. So now I will start with a brief overview of the Riemann zeta function. It is a very important function for number theory, and it is deeply connected with prime numbers. As you can see, we can express zeta for real numbers as a product of all primes p. In honor of our Swiss friends, we can say that zeta of 2 is known as the Basel problem, which is a Switzerland theory, and Euler showed that zeta of 2 is actually equal to pi squared over 6. So we have our first constant. And in honor to our French colleagues, we can say that for s equals to 3, zeta of 3 is known as Aperri's constant, which is in honor of for the French mathematician Roger Aperry, which proved that this value is irrational for the first time in 1974. And now we have our second constant. So I want to define some things first. We can say that for a random sequence, for a sequence, if the greatest common divisor of the sequence is equal to 1, we can say that these sequences are co-prime. And the probability that a given n of a random sequence being co-prime is actually equal to 1 of zeta of n. So we can obtain zeta of n if you have a true random number generator. And physics is the answer for that. So we have some types of random number generators. The first one is the most common one, which is the pseudo-RNGs, which are in everyday computers. However, they do not produce true randoms because they are based on software, and once you know how they are created, you can predict the next one. So it's really weak. So we will not use them. Next, we have the true random number generators, which are based on a physical process, but they are not based on true randomness. They are based on very difficult to predict systems. So we will not use them as well. And because we are the quantum coaches, we thought that was really nice to thought of a quantum random number generator. And this is what we use because the quantumness of the quantum theory does make us the result truly unpredictable, which is the best thing for random number generators. So you may think that the quantum device is a very complicated thing. For example, we have this beautiful technology from Zurich University, where they have a very complicated and sophisticated device. However, I will show you that we can make a device very simple that every university can do. So for this, we will explore the statistics of radioactive decay. And on a radioactive decay, it's a random process. And quantum theory cannot predict when a particle atom will decay. So if we have a constant decay rate and the events are independent from each other, we can say that we have a Poisson distribution, and we use that one. Here is an example of a real-life Poisson distribution measured, and we can see that our data will match pretty well, and I'll explain how I got it in just a moment. So this will be our experimental setup. It consists from a radioactive source, a scintillator plus a photomultiplier tube that's connected directly to the oscilloscope. So I got a little bit more details. We have a high energy photon that comes to the scintillator, and it's transformed to a low energy photons. And then it's to the photoelectric effect, we can transform them into electrons that are accelerated through the anode and then multiply, and we get our signal here. So with that, we can characterize our sample, and we can see that there is a lot of things going on here. We have X-rays, backscattering, Compton effect, and cesium gamma rays. However, the important thing to know is that all of these events happen independent of each other. So we can use Poisson statistics for that. So what's the time between two Poissonic events? And we can say that it's given by the exponential distribution, and our data match this pretty well as also. So we can further say that the probability that a random time between two events is greater than another one is actually equal to 1/2, which will be the main point throughout our presentation. So now we have to extract bits from that, and we can first assign delta T1 and delta T2, and if delta T1 is greater than delta T2, we assign it 1, and the other way around, we assign a 0. And if they are equal, we actually ignore them. So to test if our random byte sequence is truly random, we have to pass through some statistical tests. And this is the most famous one, is the NIST statistical test. And we have a bunch of applicable tests, and these results are the p-value. If the p-value are less than 1%, we can say that these sequences are not truly random, and our random sequence pass all the applicable tests, which is pretty great. So, however, we have a bit sequence, and we have to transform them into integers. So it's not clear how we can do that, because we can say that 4 bits is a number, maybe 10, maybe 22. It's not exactly clear how to do that. So the question that we want to answer is how many bits Q should be used to transform a number given a total T bits. So if you have a smaller Q, we have a smaller range of possible numbers, which have an error associated with this formula. And we have a high Q, we have increased our smaller range. However, we have a smaller sample size to work with. So we have a delta 2 associated with this error. So we can now plot the sum of these two errors and actually minimize and optimize our sequence. And for our case, we had 13,404 bits, which gave us an optimum at 13 bits per number. So now, to recapitulate what we did, we devised our device, which is composed of a radioactive source, a photomultiplier tube plus a scintillator, an oscilloscope, which actually create our random sequence. And the probability of two numbers being co-prime, we can calculate pi and a Higgs constant, which is actually pretty great. However, maybe it's a bit unclear how we can do that, so I will go step by step to an example. So here we have an example of our random sequence, and first we have to transform them in decimal digits. Then we can compare them and see the greatest common divisor. In this case, they are actually equal to 1. So we count as them are co-prime. However, these next 2 bits, we can see that one is a multiple of the another, so they are not co-primes, and we do not count them. And for z of 2, this was the z of 2 case. Now we can go back to the z of 3. We now compare them in 3 pairs. And so first we compare the first 2 and see that they are indeed co-primes, as we saw earlier. And when comparing to another one, they of course will be co-prime, because this result is 1, and then 1 and 409, the greatest common divisor is 1. So they are co-prime. So this is how we will count them. So for our results, we are trying to calculate p and a Higgs constant. We have here that there are true values, and we estimated that our error will be in the order of magnitude of 10 to the minus 2. And our results are, first for pi, we got 3.16, which is within the error that we predicted, and a pretty good estimative. And for Higgs constant, we got 1.21, which again is within the error that we predicted. However, our model has some limitations. If the half-life is comparable to the time of acquisition of our signal, we cannot approximate our process to a post-sonic event. We have to treat them as a binomial distribution. So this is some famous case that this distribution doesn't work. However, we are dealing with cesium, and the half-life is more than 30 years, so we don't have a problem with that. Now the optimization part. This work was a proof of concept. We had limited access to our labs, and we had this calculated that we use a 20-year-old student lab cesium, and if we wanted to achieve an error of the order of 10 to the minus 3, we need 2 times 10 to the 6 bits. And if I started the day that I entered the university, I would just finish last night. So it's pretty unfeasible to do. So how can we do that? How can we prove that? First, a new device with a data acquisition card or something that can collect data more easily would be really good for us. Because the main problem that we had is that our setup took 30 seconds to save a 5-second event. So we spent a lot of time collecting data. And a more active but still safe source would also increase the acquisition rate, because we had a pretty old source that only had 6 decays per in a 5-second window, which is not that good. I mean, I could take the source and put it in my pocket, that nothing would happen. So in conclusions, we built a proof of concept device capable of generating true random numbers from a spontaneous quantum process. Randomness was confirmed using the NIST test suite, and the output of our device was used to compute some famous mathematical constants, such as P and Z of 3. I want to point out that we could use more traditional multicolor methods, but we thought that this was more fun and actually more mathematical beauty. And we got a predicted error of the order of 10 to the minus 2. And optimization is possible by increasing the data set, which can be done by 2 ways. First, increasing the data acquisition speed or the source activity. And the output of your device can be used to calculate any constant that require true random numbers. As I said, for example, using multicolor methods. But I have calculated them, and I maybe can show you them later. So thank you for listening to my presentation.
Okay, thank you very much, Gustavo. So we will move to the clarifying questions from your opponent.
Thank you very much for your amazing presentation. Can you go back to slide 19, please? No. So yeah, I understand the trade-off between the size of the sample and the range, but can you please precise what is your metric delta? I don't understand that.
The what?
Delta, what does it correspond to?
Tau. Delta. Oh, delta is the predicted the mean error. Like it's a random process, so we cannot precisely estimate a error, but we can predict the mean error from that. And for low Q, for a small range, this is the error associated with it for the Z of 2 case, and this is the error associated with the smaller sample size. Like if we decrease the smaller sample size, this is how the error will behave.
Okay, that's very clear. Thank you.
Thank you. Can you just clarify how you use randomness to compute constants? So I think you use randomness to predict prime numbers, or is that right?
No,
can you just clarify the formulas, please?
Okay. Just 1 second. I'm sorry. Here. So the way that we can calculate this is by looking to Z of 2 and Z of 3. The probability that 2 numbers are co-prime. I mean, when they are co-prime, the greatest common divisor of these 2 numbers are equal to 1. So they have no, they are relative primes is another term that we can use. So the probability that 2 numbers are co-prime is actually equal to 1 over Z of n, 1 over Z of 2. So we can calculate Z of 2 in this way, and the same thing is possible for Z of 3, but comparing 3 numbers.
So 3 minutes now for the preparation of the opponent.
No, that's not me. Apportez-moi un ordi, ça marche pas. Non? Apportez-moi un autre ordi, ça marche pas.
Tu veux que je donne... Bah, je vais le garder au cas où. Ouais, ouais. Yeah. Oh, cool. I didn't see this style before. Technology, yeah. Technology. Yeah.
Okay. Are you ready to start?
Vous expliquer quelle est la valeur des formes adaptatives, juste voilà, est-ce qu'on peut mesurer, parce que c'est très bien. Et voilà, on parle de comment on peut améliorer leur setup. Et en 5 minutes, c'est bon, après, t'as le reviewer qui va arriver, donc là, tu laisseras faire, donc ça serait l'air.
Okay, Alexis, your time starts now.
Yep. So thank you very much, Team Brazil, for this amazing presentation of the #1 problem, physics of mass. So if we read the statement, you build a device, so no calculators or computer, that can be used to compute some famous mathematical constants in the most physically ingenious way. You had to optimize the accuracy of your device. Note that there are, in addition, the constant that you mentioned. So basically, I'm just going to do a quick sum up of what you did. So you both did a theoretical and an experimental progression. First, well, you explained to us that the main thing you wanted to do in this problem was to create randomness in order to have access to a zeta function. And so basically have pi and zeta of 3, which is the hyper is the number. And so you had the possibility to use a quantum system in order to have this with a radioactive decay. And so basically you validated your statement with some tests, or statistical randomness test. And so your experiments were really great too, in my opinion. So you actually did a quantum random number generator. So you could, well, vary quite a lot of things in your data, as you mentioned the importance of taking like 13 bits and how would you randomly generate those numbers. And so you verified your theory with quite a good approximation. So now, obviously, I'm going to state a little bit of strong and weak points of your presentation.
Alexis,
Sorry.
can we stop for a moment? We are not streaming on YouTube. I don't know how, so you're asking me.
Just take a breath.
All YouTube scream for my name.
You can? Okay.
It's okay?
Continue, yeah.
Thank you. Well, if you weren't following what I just said, so I did a little sum up of what Brazil team did, and so now for the strong and weak points of this presentation, so a really clear understanding of what was the problem needs in order to have those mathematical constants, the difference between a pseudo-random, a random generator, and a quantum generator that we are going maybe to talk a little bit after to maybe really have the differences between both. You studied some interesting optimization process, so we can talk about how much we can optimize this thing in your presentation. So there really were a few weak points, I have to admit, but we can underline those. In my opinion, we might want to take a time to revisit your experimental setup and maybe talk about some, I'm sure there was some really interesting parameters that you have taken into account when you did your measurement, and a discussion about the origin of your error. I think like you clearly understood and respond to your question, like there was to compute and to measure this constant, but now we are going to aim at how can we optimize and how can we reduce those error sources. Okay, and so, well, our discussion points are up there. We have all the time to talk about this, but mainly the main origins of the error source. So you mentioned 10 to the -2. I mean, I didn't really get why or where, but I think you will have the time to explain. We can talk together and with the reviewers to how could we improve. So you talked about data collecting a card, but how to increase the speed maybe by changing the system. And how can we estimate the added value of your quantum generator? I think it was a really interesting thing to not just do a pseudo or random generator, but can we quantify how much have we gained from the error, or how much, well, yeah. And so finally, maybe other ideas, but I think it won't be the main part of our discussion because it's mainly on your presentation that I want to focus. Thank you very much.
Can I share my screen? Okay. So I think you'd like me to start saying about the origin of my error.
Yeah.
Okay. If just 1 second for the transmission. Just 1 second.
Yeah. I think we can pause.
So I think I went a little bit too quickly on my error. I apologize for that. So, I mean, this is the main dilemma of our sequence. Okay. We have a finite sequence, which in mathematics is not the way to do it. Usually in mathematics you have an infinite sequence, and but we are dealing with physical process. So what's the problem? If we assign too many bits per number, we have a good greatest value for our maximum value for our sequence. However, we have a smaller sample size. We have to decrease our sample size, and this introduce some statistical errors given by this formula right here.
Totally, yeah.
And when you have, however, if you have a too low Q, we have a smaller range of possible values, and then we have to optimize this function here, which is the difference between a theoretical prediction and the maximum you can do with this smaller range.
All right.
So then what I do is I sum up these two errors, and then we can see on the red line we have a predicted curve. And we can see that the minimization occurs when the bits per number is actually equal to 13. And with that, I can estimate the order of magnitude of the error. I cannot predict the exact error because it's random.
Okay, so those errors are basically, if I understood well, the errors related to the method. Like you couldn't do less, as you have to choose between statistical and like sampling to less for your sum. But mainly, just like, and we will have the time to talk about your experimental setup. So if I understood it well, you have no errors coming anywhere from your experiment, as it's like binary.
Yeah, I mean, I can have, if I look at the measurement device, we have, of course, we have errors. However, we just eliminate these errors by assigning a 1 and a 0. I cannot have errors associated with binary numbers,
All right.
as you said.
Okay, and if we just get back to your experimental setup.
Okay. This one or this one?
Actually, the other one.
Yeah, here.
Yeah, with the oscillators. Right. So here you are measuring basically when the quantum, when the atoms are like going back, and so you really want to have the probability 1/2, right?
Yes.
What other thing could have we? What other thing could have we thought in the same system in order to have a binary random? Do you have? I mean, was it the first thing you thought about, or have you seen the literature?
I mean, no, this is a very well-known method in literature. I referenced it in somewhere. I forgot the slide reference. I'm sorry. However, there are some ways to get the bit numbers. The problem in the literature is that not many of them actually say how we get a uniform distribution from that. And this is the most mathematical accurate way to predict, to have a uniform distribution. One thing that we maybe can do is to like put a clocking device, and when we have a decay, we look at the last digit of our clocking device, and if it's an odd value, we assign a 1, and if it's an even value, we assign a 0. However, we cannot guarantee the uniformity of the distribution.
Okay, thank you very much. And can we elaborate a little bit more in the differences between, so pseudo-generator, you talked a little bit how it's not really random, but between random and quantum random, what is the main difference between those two generators?
Yeah, of course. For simulation, it's not really important, but this is a really sensitive matter for cryptography. So if we have a physical device that measures, for example, for chaotic systems, it's possible to observe this for a really long time and actually predict the system.
Yeah.
However, with quantum mechanics, this is completely forbidden. Like, no matter how much computation you have, you cannot predict the next bit.
Okay. Okay, so you really wanted to state the fact that quantum made like humanly impossible to predict.
Yeah.
Okay, and so do you have any way to like maybe quantify the difference? It's like a human between like non-human, but and sorry, I'm going to another question before the end, and maybe the interviewer want to say, how could we optimize the data collection?
Thank you for the report and for the discussion. Just two quick clarification questions. First one to the reporter. Is your error systematical or instrumental?
I believe neither of them. It's an error associated with the mathematics of the problem. It's not really a question of our device. It's a question of how well we can do with the bits we have. We kind of eliminate all the errors. I mean, they're still there, but they only contribute to our randoms.
Okay, as a question, both to reporter and to the opponent, what is your quick definition in one sentence of the physically measuring the constant as the problem asks?
Me or the opponent?
Both, like one sentence. What is it meaning for you to physically measure the constant?
I mean, I think we have to extract some data and then analyze the data to extract this constant.
So basically, the physics comes here in the presentation when we talked about quantum physics, obviously, and the beautifulness of how random we can generate things with physics. Is my response.
Okay, thank you.
Okay, so now your minute to prepare starts now.
Yes, but I don't know what to talk about. Okay.
Good. Okay, we can start. Go.
Right. Hello.
Silence, please.
So, hello, my name is Kuba Fribes. I am from Switzerland, and I will be reviewing problem number.
Okay, no, okay. Please stop.
I will be reviewing problem number 1, physics of math. I think we all know the problem statement, so I will pass on that. And my thing doesn't work, of course, because why would it? Okay, there we go. Okay, so first of all, I would like to thank the reporter for a very nice presentation. I think this was a very nice idea, very original and very cool. The choice of the constant, very nice. Using the Riemann zeta function to find both constants, very cool. The quantum random number generator, I really like that you discussed 3 possibilities and that you found out which one is the best one and you used this one. The experimental setup for me is impressive and nice ion characteristics. You continuously showed experimental data to explain what is happening in your problem, what are you trying to measure, how are you measuring it. You verified your randomness test. This is very important because you generate random numbers, but by the eye you can't verify that the numbers are random. But you checked the tests and you saw that the numbers were really random. You optimized the number of bits. I really like that because you could have just taken a random number of bits and say, okay, it's good, but you optimize that. That's very nice. You quantified the errors. This is very important because the errors are, unfortunately, one of the biggest discussion topics in this problem. Finally, you explained the limitations of the model and the further improvements were also discussed. However, I think that for the most part, your experiment is a random number generator. So even though it has physics behind it, I kind of think more physics would have been more interesting, but that's to discuss. I think that your explanation of how to get the constants from the random numbers was a bit too quick, and I didn't really totally understand what was happening. And maybe not totally complete discussion of the errors. Okay, so for the opponent, I think you did an amazing job. This is a problem that is really, really hard to oppose, and very well done. You admitted the strong points, you pointed out the lack of error discussions, some of the lack, and you started a very rich discussion. However, you did not mention that this is a mathematical way of solving the problem, and not really totally a physical way. And you also did not comment that the binomial distribution actually has some error in it. So now I would like to get to the discussion topics. Okay. So I think we can get to the overall discussion. I won't present these ideas, so maybe we can come, yeah.
So, can I share my screen? I believe that I can share my screen, right?
Yes, sure. Okay, so one of the first questions I want to ask you is using your setup, so exactly the same setup, but maybe better equipment. What is the best possible value you could obtain, the best possible precision using any equipment with the same idea?
Yeah,
and this is a question to both.
It all comes down to how much data I collect. Like, if I collect for 10 years, I'll be the impressive accuracy. However, I can improve this by, for example, the improvement that I said, changing the source and the saving method. And I believe that with a little bit better equipment, like not really expensive, I could optimize the accuracy to 10 to the minus 3 in only a couple of weeks, not 43 days.
Okay, what about because this is with equipment you have. I mean,
with
best equipment you have on Earth.
The best
you could
equipment,
imagine anything.
I believe that I can maybe get to the 10 to the minus 3 in like two, maybe 3 days.
Okay.
Yeah, it's a really interesting question, actually. I think the main source of error are from 2 sources. Mainly, the first one, the one you calculated, was the statistical one, where you're choosing your delta, the number of bits you're taking into account. And, well, this can be decreased by the fact that you're taking several numbers. That would be like really interesting. Maybe you could give us how this uncertainty can decrease with time. You said like 3 days. Maybe 1 month, 10 as a minus 4th, I don't know. And there is a 2, and maybe we can talk, it was in your discussion point, the fact that there is some kind of error with the binomial theory, and the fact that maybe there has been some physical error, like maybe the radioactive process wasn't exactly like you supposed it.
Yeah, you mean by looking at, I'm sorry? can pass through here. You mean by the Poisson distribution that we got, like this one, right? Yeah, we can approximate this as a binomial distribution. It's like a Poisson distribution. I'm sorry, it's a very standard practice, and the fact that it is not perfect is just because we didn't had a infinite amount of points. Because in mathematics, all the time you need infinite amount of points, and in physics we don't have this kind of possibilities.
Okay. I agree. So now I would like to, so you chose a way of generating those random numbers, which is your decay. Could you think of, using maybe another problem from the IPT, could you think of another random number generator that would maybe be faster and give faster random numbers?
I mean, faster, I don't know, you have to take into account the analyzing data, but I believe we can use the chaos from the looping pendulum, I'm sorry, not looping pendulum, chaotic pendulum, magnetic pendulum. I believe you can sort the chaos to generate random numbers, but they will fall in the physical category, not the quantum one, which is the best one.
Okay. What about resistor thermodynamics?
That's a really interesting point. I haven't thought about that. That's a really interesting point. I believe you could use them as the noise that you have. Actually, it's a pretty good one.
Because you have a lot of data and
yeah.
Okay. Now maybe. Yeah, I think we have to get back to the errors because I mean errors are the only thing.
I have a question to ask, and
Yeah.
I not necessarily have the answer. But do you think, like, if you we have an infinite set of numbers, so basically, does the error comes to zero, or do you think there are some physical uncertainties or physical errors that are going to give us a low value for those error for your method?
Well, I believe that when you have an infinite amount of data, then we would have to consider the error associated with the time acquisition. We had use an oscilloscope which has a pretty good
resolution.
Thank you, and the errors would be small, but when we are dealing with infinite amount of data, this would appear and mess up our statistics.
Okay, thank you.
I have a question to the reporter. You measured, one of the constants you measured was pi, and you did this basically then using random number generation. And I really like your way of going about this. I think it's a beautiful way, but I want you to answer the question, do you think there's a faster way to get from random number generation to pi?
I believe the Monte Carlo methods are the best way. We actually did it. Just 1 second, I'll get to the appendix. Here, we actually did it, the data. However, I believe that is not a boring way, but we can bring more mathematics to the problem using the zeta function. But I mean, you can do it, and for like 8 bits per number, we got a pretty close value.
Thank you. Okay, Pablo.
I still didn't get the point about your exact error. I mean, you evaluated like 10 to minus 2 and pointed out that it is hard to measure or evaluate it because we have like binomial distribution, but actually binomial distribution is well understandable and can be measured the error. It can be approximated by Gaussian distribution. It can be counted like systematical error, like some student distribution and all other stuff. So why you don't have like the exact error? Could you explain one more time?
Well, we are calculating it numerically. So we have to estimate the error of the numeric calculation. And because we are dealing with physical process, with a random process, this error fluctuates. But we can predict the exact order of magnitude of the error. And that's what I've done. I predicted the order of magnitude of the error. And I can then assign that, for example, for our case, we had 3.16 for pi. And I can say that pretty confident that this is within 0.03 from the original value.
I understand it, but we never know the exact error. We always evaluate it from data somehow.
Yeah, I evaluated using mainly this formula. You can see the delta 1 goes down pretty quickly, and as we increase our data size, our error approximates delta 2. So I can estimate, without knowing the constant, the order of magnitude of the error. I don't need to know the exact value to calculate this.
Okay, thank you.
Okay. Maybe a quick question, because you're calculating zeta function, so you can basically calculate zeta of anything, right?
Yes.
Okay, so maybe you could get something interesting out of that?
I mean, we look at that. It's well known that zeta of even values are well behaved. We have a closed formula for that. But the only interesting constant that we could take out of that is pi, because the formula is like the a famous mathematician names constants. I forgot his name. Which are numbers, Bernoulli's numbers, multiplied by pi to some power and divided by another set of numbers. And the only constant that we could take out of that is pi. And for the odd values, we know little to nothing about it. Apéry was the first one to show anything at all about the odd value of zeta function. So we don't know anything about else.
What about opponent?
Yeah, just before we finish. So we talked about optimizing. So by error, how could we decrease them? So I think we talked a lot about this. How could we optimize the device in another way? So you started to mention some data collecting cards.
Yeah, we could. I had to painfully and manually press the button a lot of times, but we could develop a circuit with a high resolution to get this data automatically. But we thought that this maybe could approximate to a computer, so we weren't sure. But we can do it with a circuit.
Great.
Thank you. Excellent discussion between all team members. So now your concluding remarks, please.
I would like to thank you, everybody, for listening to my presentation. And I would like to also have a special thanks to all the people in Brazil that are watching the stream right now and who helped me to develop this, especially Maria Emilia, who was the one who gave me access to the lab, even though I'm a first-year student, so I couldn't be there exactly. So she gave me access, and I think that we made a beautiful problem where we took the physics out of quantum mechanics and extrapolated them to create to calculate mathematical constants in a pretty ingenious way. Thank you, everybody.
Excellent. Thank you very much. Okay, we will continue with the questions from the jury members. So, Christoph. No.
Okay, thank you. First, a question to the reporter. I happen to cook well, and I can use this skill to win a woman's heart. Does that mean that my oven is a device to win a woman's heart? And how does this relate to your method, if you understand what I mean?
I think I understand what you're coming from. However, I used my device to study properties of random numbers. So these constants are associated with the randomness of something. So I built a device to get the data to study these properties. So I think that I measured physically some constants in nature.
Okay, thank you. So I'd say that if you have a random number generator, then all constants are yours. Now, a more serious question. You chose a particular method of determining zeta 3 out of your random number generator. Is it the best one? Like if you have an integer representation, for example, and you use Monte Carlo integration, would that be faster, slower?
Yeah, we can use Monte Carlo integration. We did that to some other functions, but as I said, I wanted to study the properties of random numbers. And the Monte Carlo simulation, the Monte Carlo integration, does not allow me to study these properties. It's just a mathematical manipulation of my data.
Okay. I think that I beg to disagree, but nonetheless. The question to the opponent and the reporter, very quick. Why do you care about experimental errors if they build a black box that passes all the tests for a random number generator?
Should I use first or? Yeah. No, actually, it was just the statement optimizing. So I mean, I wasn't here for the experiment. So the first thing I wanted to do is how to was it the best way you could have done? And so when I understood there was two main sources of errors in this method, well, I'll take this subject into account. But now that you are raising the point, I know it's it's kind of.
Yeah, I think that's actually a really good question. Yeah, I would say that the first part, you shouldn't really talk about errors because you have your random numbers, you verified your random numbers. So the errors, they could come from what happens later. And that's maybe what we should have gotten at too.
Yeah, so how large of a sample did you have in the end? So you had 8 bits per number, 13 bits per number, right? How many numbers in the end?
How many numbers? I have roughly 1,000 numbers.
1,000 numbers. And when you combine them into pairs or triplets, do you do like a double counting?
No. I only counted them once.
Only count, but why not twice if it's a truly random sample?
Because I think I have to carefully think about that, but I think that you'd introduce some bias because you are counting the same numbers over and over and over again, and the probability could be messed up.
Okay, and one experimental question. So you use the PMTs, were they always in a controlled environment? Because when you use a PMT for a while, the gain of the PMT starts to drift after a while?
Yes, I had limited access to the PMT, like 1 to 2 hours a day. So I collected the data very quickly, and I think that it was a controlled environment.
Okay, thank you.
I just want to talk about the experimental setup, about the source you use. You told us that you changed the source, a fresh one, and also some specific details of the setup. How can you increase the speed or the precision of the measurement of the pipe, for instance?
Okay, so for I start with the PMT.
And give me some numbers, please.
The what?
Numbers about the speed.
Oh, okay. So I first start with the PMT. It has a dead time that I have to take into account. However, our radioactive source were very weak because it's a teaching lab. We cannot have powerful sources. So we use cesium and cobalt. And if we had a very strong element, very active element, we had to take into account the dead time of the PMT. And for the oscilloscope part, we saved it manually. As I said, to save a 5-second window, I took about 45 seconds. And this mainly was the main source of low quantity of data.
It happens something else that you measured, things you measured many of these decays. And then you have the mixture, yeah? You can have a certain problem with that? And
I don't think I got the question.
The decays have a many signal. And what happened with the detector and so on, and the quantum of process there?
Yeah, so as I said, we have a lot of things going on a radioactive decay. I think that's what you're asking, right? Yeah, so because all of the events are independent and memoryless is the most accurate way to describe it. Our statistics, we can say that it's Poissonic. So we have a Poisson distribution, and then we can extract the bits with an uniform distribution. So I don't think there would be a problem with the statistics.
Short question. Can you remind me again, please, how is the Aperis constant related with a probability?
Sure. So the Aperis constant is that of 3, right? And the probability that n numbers are co-prime is actually equal to 1 over z of n. So the probability that A, B, and C are co-prime is equal to 1 over z of 3, which is a Aperis constant.
Thank you.
I forgot my question. You told you had about 1,000 numbers and they are 13 digits per number, and this 13,000 roughly bits, it's the number of bits you can collect during this 1-2 hours being able to access the lab. Did I get it correct? Okay. Okay.
So I have a question. Would that approach work if you have not really random generators? So if I wrote the codes in Python, would I also get like almost pi?
Yeah, I would get almost pi. For to have a precise estimate of pi, I won't be able to use Python, for example, because Python has the random number, the generated numbers are not always changing. They have a periodicity. So after some while, we would start getting the same numbers, and this would get in the way of measuring pi accurately.
Okay, thanks.
Suppose you live infinitely long, have an infinite number of student friends, whatever age, operating an infinite number of your setups. Are there any physical limitations to determining zeta of 3 to an arbitrary precision?
Let me think about it just 1 second. I mean, I don't think with using this method, I believe that with infinite amount of time and money and all of that, I could calculate it with infinite amount of precision that I wanted.
Hint, cosmic rays?
What?
Cosmic rays?
The cosmic rays, we also had this problem. Let me pass through real quickly. But basically, it was in my appendix. I can sort them out because I know they are very infrequently. So I can know the pulse height, because the pulse height on our oscilloscope is equal to, is proportional to the energy. And I know roughly the energy of a cosmic ray, so I can sort them out. So they don't interfere with the data.
One final question from me. It's a tough one. So when you take 3 numbers and you want to check if they're co-prime, do you do it by hand or by a computer?
No. So our understanding of the problem is that we have our device that generates some data, and this data can be used to compute some mathematical constants. That's the way so I use a computer to just check if they are co-prime.
Okay.
But thanks. I could theoretically do it by hand.
Okay, thank you very much. So please stay on the stage. You two. So the jury members will have 1 minute to decide their marks. They have asked me that you stay for their feedback so they can look at you better. And we are not showing again the grades. Are we ready? No. Okay. Yeah, we will start from. You have to raise your hand. Okay, we will start with the jury remarks.
If David is still feeling. No? Okay.
No? Not yet?
Okay. It's quite lovely approach. I actually enjoyed listening to it and taking care of all this randomness. I'm not quite sure you really need this true randomness rather than the pseudo one. And it's actually makes less relevant some part of your talk, like whether you actually need to pass the sneeze tests in order to be able to estimate your the constants. And at the end of the day, all the accuracy you get is kind of technical issues limited, and it was worth to be discussed. What I lacked in the discussion is some more fundamental things, like stuff which Christopher writes in, like, is there any fundamental limits within this approach? If we, for example, get rid of the limited access to the lab, or we try and pick the best decay source, stuff like that. I enjoyed the review. It was pretty nice done, how you introduce topics on the stage, and actually the audience actually I see appreciated it very much. But what I found it somehow putting it a bit aside, because, for example, the two-side discussion was ended as a question from the opponent saying that, okay, what we can do with optimization, what can we reach through it, and then you finish your review and you jump to new point, not actually letting those two guys to complete what they've been discussing. And it would make more sense, at least for the continuity of what we have on stage. It's not a great deal, but just I thought for the somehow perfect review kind of approach, it will help. Thank you.
I want to say that I thought this was a very nice discussion, because this is a hard problem to oppose and review. You don't know what you're getting yourself into. And I thought I wanted to congratulate you both on actually tackling it quite well. And I thought it was a very nice point that you brought up that, oh, is there any other problems in IPT that has randomness? That was really beautiful. And also well-solved problem. I thought it was an interesting approach. Overall, I thought this was a really great physics fight.
I comment for the, well, I agree with everybody pretty much that the fight was nice. It was very funny seeing everything that happened. I comment for the reporter. I didn't like the conclusions at the end, because both the opposition and reviewer did a lot of effort to make your solution to shine. But in your conclusions, which is the final word that you have, you did not say anything about the problem or what is to be done in further research or whatever. And also I like a little bit of the intuition of, or the geometry behind this relationship between a constant and physics, or between a probability and a constant, which is kind of strange. But overall, I think it was a good fight.
Yeah, okay. So yeah, I enjoyed this very much. I especially like the fact that you chose a system that can reproduce two constants. I do not think you have a truly quantum generator. It's like an intersparsed quantum and probably something probabilistic in it, but knowingly probabilistic. Having said that, it doesn't really matter, because you did obtain a random sequence. The only remark I thought I had was that you would need to use the computer to compute everything in the end. And even though, yeah, the problem statement allows this, but I think that you don't even have to, right? You could do all the calculations by hand. That's why I asked the questions about the number sample. So for 1,000 numbers, you can do that. And yeah, for the opponent and the reviewer, I enjoyed the review. It's a Kuba talk show again. Yeah, right. Yeah, yeah. Yeah. I know it was not simple for the both of you, so congratulations. Yeah.
So I would like to say that I am ultimately unimpressed with the approach of using a random number generator to calculate two constants, because every constant that you can think of can be taken out of a random number generator, and probably the entire physics. Okay, I have to say that this physics fight was this part of the final was pleasant to watch, but I'm not factoring the fun factor into my grade. So I would like to say a few harsh words to you with the understanding that I really appreciate what you did. So I think that a large part of the discussion was meaningless. I'm sorry, and it was very explicit at some point when Kuba ran out of ideas, but instead of finishing this part of the of the fight, he just changed this discussion into everyday banter of physicists. I mean, like, I take it as a meta message about this discussion. Thank you.
I just have a question for the jury board, and is if there are true quantum random number generators.
Okay, maybe I will do something very bad for my future career because I will disagree with my dean. So the thing was that I wanted to talk about is that I wanted to check the proof about basically this 1 over zeta function being the odds of taking a coprime numbers. I Googled it, and this basically has a one swipe of text. So it's not a lot to read, but basically I couldn't manage because the discussion was so great that I just couldn't get into it. I was just listening to you guys. So I believe that this is a very well done job, especially, well, that we just get into the point that we are listening to you. And in my case, I'm listening to you because you have something very interesting to say. So thank you.
Okay, I think that we have finally finished after those really tough remarks. But anyway, so we'll have a very short break, 5 minutes break. You know, you wake up, break your leg, and I will drag you here to the auditorium back if I have to, so please.
Algo que hizo otro muchacho del otro fue el coche cortado. La dejó el contador de 1 a 0. Entonces no puedes aparte de que se hace la operación. Si no es una calculadora, puede ser, ¿no? No, pero algo.
You know, like clarifying question was more for
Yeah, I know, like
a bit more of a like as soon as
it's not
it was
like
a
a
bit
discussion. Yeah, I know.
at the first I thought, okay, maybe it's okay because they're just clarifying what their definition is. But then it became into like what I think it should be.
I know.
That one was a bit hard, sorry. Yeah.
No, don't worry, don't get about it.
It's just because I felt it might have affected the discussion a bit.
I mean, at this point, it's not as important.
Got a good score for reviewing, so it's a 9.17. But yeah, you're right. The report was not as good.
Well, you have to see. You still have one more round, but.
Close, actually.
Yeah. Okay, can we get back to our seats, please? Okay, we need to start the third round, please. For all teams, Team Brazil, Team Switzerland, Team France. Sorry, thanks. Hey, Team Brazil, where's the rest of your team? Okay, but one, just one. Alexis, where's the rest of your team, please? The other member of your team? We need him? Thank you. But I don't listen. Hey everyone, we need to start again. And Team France. Probably, yeah. We'll keep it that way for the final. I know, but maybe we can ask them to, help a little bit. Team Brazil. Good. Okay, no problem. You go back, like you take it and you go back. Como una horita pasadita más. I need you to go back there.
Human talking with I've never seen that. Never, ever, ever seen it.
And it actually helps. I believe my experience that whenever anything emotional happens, it helps keeping, like, reminding yourself that why we're here now and
I think we're showing this. We're being positive. That's full position. Even if I think it's not different not to have been okay, I thought we were going to see I would like to say after, but not with the person, just a general comment. I can discuss with them if you want, but I don't want to make this about my friends. I would rather talk about this without my friend even knowing than everyone being able to, yeah, maybe. But everyone being really, but after a fact, when everyone's thank you very much.
Thank you for understanding.
Thank you. Okay, so Anastasia. Thank you. So we can start our third and final round of the final. Finally, ooh. So now for this round, France will be the reporter, Switzerland the opponent, and Brazil the reviewer. So please, Team France, you have 5 minutes to prepare. We good?
The broadcast?
Seems. Do you want to start?
Thank you very much. And yeah. Am I okay here, or shall I go to the other side?
Okay, you can.
I'm ready to go. Wait, stop. Wait.
Silence,
So
everyone,
thank you very
please.
much for your attention. I'm so happy to be here presenting the droplets and the fingerprint problem. Thank you to all of you, the audience, the jury, and people who are watching from YouTube. I hope you're going to find it interesting and beautiful. So let me read the problem statement for you. When droplets fall on a surface covered by a layer of sand, interesting patterns are formed. We have to study the formation process and then talk about what parameters of the droplets can be inferred from the resulting crater. So to start with a short outline of the problem, I'm going to talk about the experimental setup, then the formation process, then the impact of the relevant parameters on this process, and then tackle the inverse problem. So first of all, a short sneak peek of what we used for our setup. We had here a syringe full of colored liquid, a LED screen, and our beautiful high-speed cameras. and a layer of sand, which was also very costly. I mean, don't forget it. So we have the droplet which is falling here on the sand, then it forms a pattern. Let's see a video of it. So here you see a drop which is falling very quickly, and here some droplets of water are expelled. So the problem parameters here, we have many of them. We're going to try to study as much as we can, both theoretically and experimentally. We have the impact speed, obviously, the diameter of the drop, the sand grain size, the impact angle, the viscosity of the fluid, and the type of fluid also, and the surface tension. Forgot to mention it. So I'm going to run a general study with water, and then I'm going to study the other parameters in a second time. So to start with, we have 3 different regimes we can see. We have a low-speed regime where the drop falls, and then it expands, and then retracts completely, like such. We have a second regime with an intermediate speed here, where the drop expands, but then doesn't retract completely. There's a phenomenon which is called freezing, which means that the sand gets trapped within the water, which increases the viscosity of the water, and the retraction is not complete. So freezing or jamming if you prefer ice creams or jam, as you wish. And then at high speed, you have a big expansion and the retraction is very incomplete. And at a certain point, the droplets of water are expelled and we see this fingerprint pattern appearing, which does not appear at lower speeds. So the phenomenon physically is very clearly understood with a competition between two main drivers, the inertia and the surface tension. The inertia wants to expand the liquid when it falls, and the surface tension wants to maintain the cohesion of the liquid. So what we see here is what I just said. So the inertia wants to open the drop, tear apart the drop, and the surface tension wants to make it cohesive. And so we have those three different regimes, and we can try to understand what is the boundary between the two, and we can introduce the ratio of these two drivers, so the surface tension and the inertia, which is called the Bond number. The Weber number, sorry, thank you. Then we can look at the impact shape of the drops. We can plot it with the velocity or the Weber number, which is the same, they're related quadratically. And we see here the first regime, the second regime, and the third regime. So the size of the droplets after it has fallen dramatically increases with speed. And this is because the retraction is jammed or blocked by the increase in viscosity by the sand. Now we can look at the spreading speed here. So here I have plotted with three different Weber numbers, so higher speeds, blue, red, green, blue, green, red. And we see that the radius increases more obviously when the speed is higher, it increases faster, and the retraction is lesser. Now let's try to find a model for this. First of all, yeah, with smaller drops, we see the exact same behavior. The only difference is that we do not see droplets being expelled at the same Weber number. So for a same Weber number, less droplets are expelled when the drop is smaller. Which is logical because you have less fluid, so for the same speed, you see less droplets expelled. So, and for larger grain size, we have the exact same behavior too, only the pattern here is a little bit less visible between the three regimes, but we see also these three regimes with larger sand grains. Now, the first model for the speed of the droplets, we can have an analogy with the fall of a droplet on a plane. So in this case, we're going to neglect friction, and then we're going to take into account afterwards. So if we have a drop that falls on a plane, you can use the Euler equation. You can neglect gravity during the time of the impact because it's very short. And then you can derive this relation that gives the Dmax is the maximum radius of expansion of the drop, which is related to 1/4 of the Weber coefficient, which is related to velocity. So here we have a relation between the maximum expansion of the drop and the velocity. And if you want a demonstration of this, it's pretty quick, but I like to insert some theory also, this problem, because it's, so as I said, you neglect the gravitational field, you take the characteristic time of the impact, and using only volume conservation, you get to this relationship. That's Euler and volume conservation. And this enables us to plot in a log scale the Dmax, so the maximum radius of the drop when it expands, with the Weber number. And what we see is actually a plot with 1/5 and not 1/4. And this is something which is broadly discussed in literature, actually, because these different coefficients takes into account the dissipation forces, and in particular, the energy needed to eject the sand grains from the impact points. And so we have read several articles which really detail this difference between 1/4 and 1/5 due to this energy dissipation. And we can make an analogy with the craters also on moons, which is, we see a similar phenomenon too. Only on moons, the energy is not dissipated by ejecting the grains, but by thermal shocks, thermal waves. Now we have a second trend here where the radius remains constant, and you may wonder why, and this is because some water at that point starts to be ejected. And so the radius no longer increases. What happens is that the droplets get ejected. Now for smaller drops, we have exactly the same behavior, and actually this law holds, in literature we found it holds for several dozens of liquids, no matter the grain size, almost no matter the viscosity, and almost no matter the surface tension. So we have tested this experimentally for smaller drops. Here it holds very well. For a larger grain of sands, it holds very well. And now I'd like to talk about the second parameter, which is viscosity. So viscosity, you can understand here that with water, the main driver of the retraction is the surface tension. But obviously with honey, you could say, well, it's not surface tension, it's viscosity. So what's the boundary between the two? And we could also actually compute the ratio between the Weber number and the other number which relates to viscosity, which is the Reynolds number. And here, if you take the ratio of the two, you get a ratio which is much larger than 1 for water and much higher than 1 for honey. And in this case, you see that you know the main driver of the phenomenon. In the case of water, it's surface tension. We can also note that the viscosity, what it does, so first of all, if it's very high, it reduces the expansion. If it's very low compared to surface tension, it doesn't do anything. But another effect of viscosity is that it reduces the volume which goes into the sand. And here we can demonstrate this is from the Washburn's equation. So you take the time it takes for the fluid to go into the sand, and if the higher the viscosity, the lower the volume of fluid going into the sand during the expansion phase. Now, as for the fingerprint patterns, which give the name to the presentation, we see here that we can explain them. We can go back on that later if you want to. But we can explain them using, actually, again, the Washburn's equation and then the Reynolds number with some approximation taking the characteristic time of the impact as the natural free oscillation period. And with this, we can get a model for the number of fingerprints in function of the speed. And here we were able to fit our data quite well. But there are two phases. There's the first phase where there are no fingerprints under a certain velocity. And from a certain point, we see this trend when the fingerprints start to form and are more and more numerous. Now, for sunflower oil, we have the same kind of behavior. As I said, it's less viscous and less surface tension, but we see the same kind of behavior, only the retraction always happens because there is less interaction between the sand and the fluid. And as I said, oil verifies this law too. Now, on an inclined surface, we were able to devise an equation that relates actually, if we have an uncircular impact, obviously we can find the axis of the impact, which is the inclination axis. And then we have also devised a formula with relating the eccentricity, the arc sine of the eccentricity to theta, which is this angle. So, yeah. Now, I'd like to tackle in the 2 remaining minutes the inverse problem, which wasn't the subject to. Using all what we did here, we can tackle the inverse problem. So first of all, here we see the droplets. What is this droplet? First of all, we can have access to the impact speed, and firstly, without an angle. So it's not working. Okay, it's not working. So first of all, the impact speed is related with the Weber number. I can talk with when it's not working. So we have the Weber number, which relates the impact speed to the diameter of the crater. Sorry, the diameter of the maximum expansion of the drop. So we can measure this diameter, and then we can get access to the impact speed. A second thing we can do is we can use okay, and then we can get the oh no no. Sorry for this. It's no problem. Okay, thank you. Thank you. It's perfect. So yeah, next slide. It's not working. Okay. I'm really sorry for this. Ça marche pas? Attends, ils ont bloqué le temps. Can we take a timeout? Yes. Yes, thank you. No. Okay, let me just finish without the presentation. So, as I said, we use a Weber number to relate the velocity to the highest diameter of expansion. Then we can get also the mass of the fluid by just weighing the dry sand and the wet sand. So if you take the impact, you weigh it, then you let it dry, and like this, you can have access to the mass of the drop, which falls. Yes. And then with this, we can, so if we know the mass and if we know the size of the impact, we get access to the velocity. And then we can also get access to the impact. Okay, so here you see we weighed the dry and the wet sand, got access to the mass. Then we measure the impact diameter, get access to the velocity of the impact. Then we can also have access to the impact angle. The axis is the axis of tilt. And with our linear relation, we can get access to the impact angle. So to conclude, we had three different regimes. This relation with the Weber number, the impact angle, and then we were able to tackle the inverse problem, having access to the mass, the speed, and the angle of the drop. Thank you very much for your attention.
Okay. So we'll continue with the clarifying questions from the opponents.
Here. Okay. Several clarification questions. First of all, have you measured the depth of the crater?
So there is, yes. So what we do is that we take the layer of sand, which is much higher than the depth of the, much larger than the depth of the crater. So there is no problem on this point of view. And the second thing is that the depth of the crater is pretty constant, actually. Most of the energy is dissipated on the lateral spread of the sand grains.
Have you measured it?
Yes.
Great.
I'm saying it's pretty constant.
You have observed only 3 different patterns, right?
No, yeah, it's regimes, yeah.
Have you observed jets during, like, you have high-speed camera, of course you have access to all the process, like, have you observed the jets on the video?
You mean the water which is expelled from the crater?
I mean, like, water is expelled and then it collected back, maybe there's like a jet.
Okay, so there are two, as I said, in the highest velocity regime, you have some droplets which get expelled. At the beginning, no, and I can show you as a video of the retraction, you mean, or the expulsion? The drop never gets...
Slide forward.
Yeah. Yeah, you mean that video, yeah.
No, forward, like further.
So that's, I thought slide 4.
No, further.
It's not working, sorry.
Okay.
So as I said, but to clarify, you mean you want to know if the drop can get out again of the crater? Yeah. No, there is not enough energy for that.
Was the diameter of the droplet a parameter? Did you measure it? I didn't get it from your presentation.
Yes, so the diameter of the droplets is a parameter we were able to control. And so it relates to the volume of the droplets, yes.
Sorry?
It relates to the volume of the droplets, and we were able to control it with a syringe.
Okay.
We imposed it, yeah.
Yeah, thanks.
Je t'ai demandé quelque chose. C'était combien le diamètre?
En fait, non, ce qui se passe, c'est que ça dépend du sable, mais si ton sable il absorbe rien, typiquement des billes de verre, si tu as des billes de verre et que tu n'as pas de sable, la goutte elle tombe, elle s'étale et après elle saute.
Ouais, c'est ça.
C'est ça dont il veut les
D'accord,
parler.
ok.
Ils utilisent du sable mais pas des billes de verre.
D'accord. Ok, mais le diamètre de l'impact, c'est 1 cm à peu près.
Sur le fait que tu as dit que la hauteur était constante, alors qu'en plus sur la photo, ça se voyait bien que c'était pas constante. En gros, donc, tu dis que ça peut être un paramètre, là, c'est là, et tu dis c'est vrai que c'est pas quelque chose qu'on a fait parce qu'on a pas beaucoup de procédures.
Ouais, c'est ça.
On avait des très grandes incisions, mais on comprend que at really high speed, you have a tiny. Oui, at high speed, tu as un tiny. T'as une tiny depth de la goutte, parce qu'elle s'exprime. À low vitesse, t'as
D'accord, je sais, mais...
Tu peux être vu dans l'envie, bien, bien. Sauf pas trop bien dans l'envie.
D'accord, ouais.
ladito de oponente. No. Do you want to start now?
1 minute.
Okay.
Okay, I think we can start.
Go ahead.
Hello everybody, my name is Pavlo Koshko and I'm representing Team Switzerland, and today I will oppose the problem number 10, droplets and fingerprints, with a beautiful solution from the team of France. Okay, just quick reminder of the problem statement. Here are two main problems, like study the formation process and inverse problem, what parameters of droplets can be inferred. Here I want to point out that droplets fall on the surface covered by a layer of sand. Okay, let's go on. We have seen a really beautiful presentation of the Team France. They have used really two high-speed camera to watch it from upper and from side, maybe even from other side, like all 3D 3D visualization. It's fantastic. I'm really appreciation for it. And like we have seen great animation. Low speed, high speed, all possible options. I think they have made dozens of videos. We have seen like intuitive explanation of the phenomenon, which is good to understand the physics behind the problem. We have seen the three difficult patterns because as in this problem there is not just one pattern that can observe, there are a lot of them. With it like three different, is super cool. They varied also types of liquid and scents a little bit. As I have seen, it was like a honey, it was the water, a little talk about viscosity, it's cool. Also, what is important is not stated directly in problem, but they have do it. It's angle dependence, which is super cool. It's not so difficult, but easy to do. Like, thank you for doing it. Actually, also a little prediction of patterns radius, and of course, inverse problem was solved. Now about weaknesses. We have seen no discussion about depth of sand, and it is a really important parameter here because droplets, they fall on the surface covered by a level of sand. So like I feel this quite important, and maybe it will produce different patterns completely if the layer of sand is thin or it's thick. And we have seen no discussion about it. It would be nice to have this during discussion session. Also, like influence the surface under sand. What if I change table by the paper? Would it change something? Also, we missed another possible patterns that can be observed in this problem, and we will discuss it later. Videos were a little bit dark, so it was seen the main patterns, but it was really difficult to see the main observation. I mean, like high-speed camera requires a lot of light, but if you have high-speed camera, you can put more light on the sand to observe it. Also, only two liquids were researched in this problem, and no real theoretical explanation of the pattern formation was given, which is things that I wanted to see in this problem, how it's really, we have qualitative but don't have quantitative explanation here. Also, different types of sand were like mentioned but not really discussed. I want to have more discussion of it. And during inverse problem, viscosity and surface tension were not taken in account. It would be nice to hear a reporter's opinion on it. About ideas for discussions, there is a lot because I really find this problem really interesting, and there are a lot of topics to discuss here. For example, how to distinguish possible patterns. You mentioned that Weber numbers is important. So what are critical values of Weber number to distinguish patterns? So pattern is made of water, or like intuitively it can be things that air is compressed underwater, it can be spilled the sand, or it may be other pattern. So what is qualitative, at least, explanation of this? What about depth of sand? Is crucial parameter or not? What about surface below? Influence of viscosity, it was told that we have not observed patterns, but like I maybe want a little bit more discussion what it changed. Of course, other liquids and other sands would be nice to see because, in my opinion, bigger granular sand may really change effects significantly, but maybe not. I would want to hear the rapport's opinion on it. Of course, temperature somehow can change the effect, so it would be nice also to hear like few words about it. Also about depth of sand, continuing, like does the water always reach the surface or it's standing upper on the sand? I mean, it can be important for patterns. And about other patterns, as we have seen on the photo provided during the problem, there is one pattern, another pattern. This was not studied, in my opinion. Also, like this pattern, also I have not yet observed in reporter's speech, and maybe just a circle. Like, it would be nice to discuss all these things.
Okay, thank you very much. So now the report.
Well, so thank you so much. I think you have raised some very interesting points for the discussion, really. The one I wanted to continue exploring, so thank you so much. So first of all, well, for the other, I'm reading here on your computer, for example, other liquids. So we did investigate oil, the only other liquid. So we investigated water and oil. Oil has a lower surface tension than water by a factor about 1/2. So the difference we observed is that the retraction was easier. So the retraction of the droplet was easier with oil than with water.
Okay, I want to like mention what is critical Weber parameter to distinguish at least 3 patterns that you observed.
Exactly. So all the Webers were above 100, which means that the kinetic energy was much higher than the maximum interfacial surface energy. And then the boundaries between the 3 regimes were about 200 and 400 Webers. We can see it on the graph.
And you have mentioned 3 patterns. You really observe only 3 patterns? I mean, even on the photo provided to the problem, there are much more patterns.
So we can have more patterns if droplets get expelled from the crater. But what we observed in terms of the crater formation, the main crater, we observed only, as I said, those 3 different regimes. But
I would partially disagree because, like, if you put let's put 2 critical regimes, like very small height and huge height.
Yes.
Like, could you explain 2 patterns that you will see here?
Exactly. I would like to come back to that because, and especially we have a theoretical model. I went on very quickly about the pattern information, but I think, thanks for pointing that out. I'd like to investigate a bit more if you're okay and answer your question. Yeah, I'm going to go to the...
Yeah, super basic question. I'm using very small height.
Okay,
what
so
pattern
the small
would I observe?
height, you will only see a little crater with no fingerprints and no water expelled. Now, if you go from super high, your drop is going to explode on the surface and be torn apart. You're going to have many different droplets expelled from the crater.
Okay, thank you. Also, you mentioned like when you was calculating the speed of interaction, you neglected friction.
Yeah.
So you think the air friction for droplet is neglectable?
Yes, we have an annex for this. So this is verified experimentally. Can I do it? Sorry. So it's here. So here you have this table where thanks to the high-speed camera again, we were able to measure the speed and fit it with the well-known law here. But
thank you for clarifying. Yeah, now it's obvious that it's neglectable.
But I also wanted to clarify another thing you said, which is very interesting, is that so when you come from a very high height, you can, or in our case, the droplet exploded in many different droplets, but depending on the type of sand, you can also have a very big impact, and also depending on the viscosity. For example, if you take some honey or a more viscous fluid and drop it, it's going to get into the layer of sand and not explode. So it really depends on the Weber number, typically, for example. And
okay, thank you for clarification of this. Weber number. Why you choose the Weber number? I mean, there is other number of drops, for example, on a Zork number that took in account viscosity, because Weber number does not take in account viscosity, we could create another number. For example, a square root of Weber divided by Reynolds number. It's called Ohnesorg number.
Okay.
Maybe it would be better to explain the model with this number, at least qualitatively, because you don't have, I think, like super theoretical model.
Can you? Yeah, I'd like to show my theoretical model for the pattern, which is maybe not super, but I think quite solid. I didn't have the opportunity to talk about it.
Main question was Weber number or Ohnesorg number or other numbers?
So can you write? I don't know. Can you write the number? Because what we used were a combination of the Weber number and the Reynolds number.
Could you show where it is using?
Sure.
The main idea is that use viscosity also in the number, so took in
here
account.
you see here, for example, because the Reynolds number takes into account viscosity, and the Weber number takes into account the surface tension.
Yeah, have you like used this equation to fit data or somehow?
Yeah. So for example, so the Weber number, it's the main number we use it to fit data about the water, because as I said, it's the effect of the surface tension is predominant. Now for the Reynolds number, we used, we fitted here. This is very important. If you give me 10 seconds to talk about the fingerprints pattern, well, we don't have time, but yes, we used the Reynolds number to fit the number of fingerprints.
Very last question, depth of the sand.
The depth of the sand, as I said, is much higher than the depth of the crater. So a
but
few centimeters.
Do you feel that it is not like stated in the problem, the droplet fills on the surface covered of the layer of the sand? Because if you see the picture provided in the problem, it's like... Okay, we will continue during manual discussion.
With pleasure.
Now to the clarifying questions from the reviewer.
First, thank you, reporter, for a very good presentation, and thank you, opponent, for a very good presentation and discussion. For reporter, how did you vary and control the thickness of your sand in your experimental setup?
So the thickness, as I said, is fixed. It's several centimeters, and so it's much higher than the maximum depth of the crater, which is the order of millimeters.
Could you see if the sand was loose or very compacted?
That's very important to point this out, thank you. So it was quite loose. If you have a very compact sand, the behavior is very different.
Okay, could you clarify me, for what parameter you obtained of the droplet from the resulting crater? I did not understand well your inverse problem.
Okay, yeah, great. I'm sorry for the technical issue at the end. So we could get the mass of the droplets, so the radius of the droplets, the speed, the impact speed, and the angle of the droplets.
Okay, thank you. So when we look for a crater, what do you look for to describe the droplet that formed it? And for opponent to, I repeat, when we look for a crater, what do you look in the crater to talk about, to describe the droplet that formed it?
So the first thing you want to do is look at the weights. If you can extract the crater and then weigh it when it's dry and when it's wet, so you can get the measure of the water and approximation. Then you can also have, obviously, the maximum size of the crater, which gives access to the velocity. And then you may want to look at the semi-major axis of the crater to get the angle.
Okay, except surely reporter is right of parameters I could extract. I'm thinking also we could extract the wet sand, we could measure its volume and use empirical data to solve the inverse problem. Also, there are different patterns, so from the type of the pattern we could find the Weber number. Also, we should measure the layer of sand to be able to extract parameters.
Thank you, no more. So.
Thank you.
we can discuss that.
Okay, then you can start now.
Sorry for this problem, guys, but I'm João Pedro Menquilo, not Leonardo Falabella, and there will be the review for problem 10, droplet sand fingerprint for Team Brazil. First of all, let's remark some positive and negative points of the reporter presentation. He identified very important parameters of the crater in the droplet, and he varied all very parameters of them. He showed the relation between the Weber number and the diameter of the crater and the maximum diameter of the droplet. He's made an analysis of big and small droplets, and it's a very good point to point out. He did a detailed investigation of crater formation and showed us very good videos and the photos to see the complete phenomenon. He did a very good controlled experimental setup, and he could obtain very good results of that, especially because of the fast speed cameras. And he measured the spreading factor, the spreading speed of the crater formation. But some negative points: he did not vary humidity of the sand, wettability, and the packing fraction. And as he said, he did not vary the thickness of the layer of sand. He did not explain how thickness of sand and the layer was important, and if it was controlled, but he clarified me that in the technical questions. And he did not clearly explore hydrodynamic values in the inverse problem. So was the problem solved? Yes, but more parameters could have been explored of the droplets from the resulting craters. About the opponent, he acknowledged the high quality of the presentation of the reporter. It was a very good presentation, and I agree. He observed such a lack of discussion of the sand depth and the properties that can be obtained about the depth profound of the depth crater. He highlighted the weakness on the inverse problem solution, and it's a point that we can discuss. And where about air friction, it was questioned about for him. But some negative points that he not explored: did not question about the experimental setup control, did not focus on the parameters of the crater and their relation to the droplet, and he could have established the difference between inner and the outer crater. So I think we have some points to discuss, such as the thickness of the sand, and it's important, the wettability, the sandy humidity, and and think some other points that we can discuss right now. So, such as if you have a random droplet, what could you obtain from that, from the resulting crater fit? And since you have, thank you. I think opponents was trying to discuss about the thickness of the sand before the discussion finished, and I think we can bring up the
yeah, I think it was one of the main point of the problem, as as we have seen patterns on the photo due to the problem, and most of half of them were produced with interaction with the surface. We have seen surface, so the water reached the surface. So question to the reporter, is it important, or and why you haven't studied? Maybe it will enrich your understanding of problem.
Very good. So yeah, it's a very good question. So yes, it does matter, obviously. So our study was in the limits of a high height of sand compared to the depth of the crater. Now we can have a very thin layer of sand, And in that case, it really depends on the underlying layer you have, the underlying material you have.
So on material also depends.
Yeah, I think so. So for example, if you have a very thin layer, all the sand will be ejected, and then what we studied was not a very thin layer, but we studied no layer of sand, so only on a a surface, normal surface.
Yeah, very thick one.
And so this, it really depends on the surface. But for example, you can have the drop retracting and coming up again, or exploding.
Okay.
And
one more question I want to bring out in discussion. That this small droplet that we've seen, their number, how it is correlated with the big drop? What is the condition to make these small droplets? And could you describe like how many of them, maybe to some symmetric function, some?
Absolutely, can answer. It's a very good question, I think, and it also related to what you said on the model. I'm going to try to go back to my equation. As I said, we can use. Let's try this. We have a model for both the fingerprint pattern and the number of droplets. This relates to, as I said, the Reynolds number. You can think of it's an instability actually. So you can think of Rayleigh plateau of instability, obviously. Which gives the capillary length. And here I have the demonstration. And here, okay. So here you see you take the Reynolds number, and then you take the characteristic thickness of the jet, which is created, and then you use here, this law for the infiltration, which is square root of t. And then here, there is an assumption which is made in literature usually that the period of time, the characteristic period of time of this phenomenon is related to the free oscillation period of the phenomenon. This is something we find in literature. And with this, you can use, and the Reynolds number, you can get access to this law, which gives a relationship between the Reynolds number and the Bond number. I admit it's not very clear here. And the number of fingers and also the number of droplets. But
can I ask number of fingers? It's 2.8?
No, it's not scales, but this, yeah. But actually, you have a law which is power about the power you see here. But physically, if I can get some physical insights, is that you have this instability that after a certain energy ejects the droplets.
Okay, maybe next point that would be important to discuss is humidity of air and humidity of sand, how it influences the effect.
Yeah, I agree with that, and I would ask you for the reporter and for you to what do you think would affect the crater by humidity? First, for our reporter, please.
So yes, as I said, when we weigh, this is very important. When we weigh the sand to get the volume, we need to also dry the normal sand, because if not, we have a problem. So we have to be very careful. When we weight the wet sand. But after that, when the humidity increases, the sand is more compact, and so you see a very different pattern. Actually, it radically the water goes more into there is less splash out. I mean.
So it goes more in the sand when it is wet?
I think so. I believe so. We didn't run a lot. So it was just qualitative, but I'm not sure about that.
I believe that humidity of sand, of course, changed significantly the effect, because another interaction, and maybe the reporter, as I trying to talk, like there are two effects. Maybe the crater is form interaction with water, but maybe it's about air that go out of the drop. So it would significantly change the second effect, because the air would not be able to splash the wet sand. So of course it would be another pattern.
Yeah, I think the interesting point that we talked. Please, I saw your images of the crater using different sands, different granulometry. Do you think with a bigger grains, could you obtain the same patterns, or it's not exactly the?
That's a good question, and yes, not exactly was my short answer, and it relates to what you said. The compactness of the sand is very important, because if you compact the sand, you have a very different pattern. The sand behaves more like a surface, a solid surface, when it's very compact, whereas when it's very loose, it doesn't behave like this. And when you take a bigger grain, you have much more space for the air inside. So it behaves less and less like a solid surface. And when you take a limit case where the sand is enormous, then the drop just goes into it.
I think I have a question for... No, please, opponent.
Because I see that normally, if I didn't make a mistake, D0, the diameter of the drop, is a parameter you fit?
Yeah, or? No. V0 is we choose it.
Okay.
And then we fit this, yeah.
Okay, so you Don't you think investigating the initial diameter was a good important part of the
Yes,
question?
we did it for a few diameters. You see here comparison with smaller drops. We took some smaller drops, and what we did is that we see the same type of pattern, but less water is ejected. This is only sand. But to get droplets expelled from the crater, you need more speed.
Okay, thanks. And then I had just maybe another question. As I've seen a few points that are outside your fitted lines. Do you think that maybe monitoring the temperature of the water, and because we've seen the dependence with viscosity, so monitoring the temperature of the water and maybe also the humidity in the room could improve these results, or maybe did you already do it?
It's a good idea. We didn't do it. We just tried one time with hot water. But the viscosity changes a lot with temperature, so it could be an additional parameter.
Please refer to.
You were discussing crater formation and the diameter of it. Do you think there's a difference for both teams between the inner crater and the outer crater? I don't think we've had this discussion yet.
So the question, is there a difference between inner and outer radius?
Yeah, is there a difference between an outer crater and inner crater?
I mean, in several patterns that we have observed, there are like two circles. Not at all, but in several you can observe how I have shown. There can be inner radius and outer radius, and of course there is correlation between them and between the radius of the droplet.
Okay, so yes, I would like to add to that we can see some interesting shapes within the crater. So when you have a low velocity, it retracts, but when you have a higher velocity, you have this kind of bump here, which appears, and which is due to the sand retracting in the center and not completely on the side. So you have this kind of two type of crater, maybe an inner one and an outer one.
Can I ask about the wettability of the sand? Do you think if you had a super hydrophobic sand, will the craters be formed equals or the same way? And for your opponent too, please you could clarify.
So we tried this with, yes, not a sand, but a synthetic material. And it's the behavior is completely different. So first of all, the surface tension is very high. So you have very round droplets in the end. They don't get into the medium at first, and they can even bounce back, I think. They can even rebound, yeah.
I totally agree with reporter. There's video on YouTube how it is bouncing back, and it's very beautiful effect. And the very last point that should be deserved to discuss is the analogy with the crater on moons or other asteroids that could be seen as granular material taken together by gravity. It was mentioned by the reporter, but I feel that it should be discussed more.
Actually, it's very interesting. There are two very close phenomena. Which is very interesting here is that here 97% of the energy is dissipated by moving the sand. And in asteroids, 97% of the energy is dissipated by thermal energy. So we have two different types of dissipations, but the ratio of energy dissipated is the same.
Super. Thank you.
Excellent discussion. So now we have the concluding remarks.
Okay, so first of all, I'd like to thank you all. Thank you to the jury, the audience, people watching, and the opponent and the reviewer for what I believe was an interesting discussion and the many different parameters we had, investigating more into depth the theoretical model, the different types of pattern, also shedding lights on some of the parameters we could have studied more. And I think this is really the basic of scientific work. And so I would really like to thank you for that. Thank you for your help. And thank you for your attention. And thank you for this tournament.
Woo! Okay, excellent. Thank you very much. So now we go to the juries.
A question for the reporter. So this is an inverse problem. If your teammate was to drop a drop of water in your system and tell you the mass was this much, with what precision can you actually estimate the velocity?
The velocity, okay, between 10 and 20%, I'd say.
Okay. Yeah. And does that change in different regimes?
Not really, I'd say pretty constant, but yeah. It's not extremely precise, but we get a right idea of the velocity.
Sorry. Quick question. On all your experience of looking at these patterns again and again, if I give you a pattern without the element in it. Can you distinguish what kind of liquid was there?
Yes, for example, if you see if total retraction and a huge crater, if you tell me it was a small volume, I can say, for example, it was more oil than water. And then, for example, if I see no fingerprints, I can think that the speed was lower than if I see some fingerprints. And obviously, if I see some droplets on the side, I can tell the velocity was very high. And
So your brain actually solved the inverse problem.
yes, it's the habits of doing it.
Hey, that was one of my questions, so I'll have to come up with another one. So the problem statement is droplets, so I presume anything. Have you considered what happens if you drop something that could have a chemical reaction with the sand?
Honestly, I didn't think about that, but it could be very interesting. Maybe a bomb to explode the sand or something.
Flour. Oh yeah, water and flour is a nice example. Thank you, Christophe.
Okay, yeah, then it will be completely different.
Or sand is a silicate, so you've got all sorts of lots of
That's
stuff
a good
to experiment
idea.
around with.
Thank you.
No problem.
Okay, I have a series of questions. I hope they are easy. First, you recreated many of the experiments that are already described in the literature. I appreciate your effort in exploring, but I'd like to know what is entirely new.
What is?
What is entirely new about the data and also about the theory?
For example, the angle of impact, I didn't find it anywhere. I think we invented that. I hope it works. So that's the first thing. And then we really tried to have a broader study. We used several papers, obviously. But what we did here, was putting together all different elements to solve the inverse problem. And then some bits of the theory were also of our own. So some theory, some experiments, the angle of impact, and weighing the sand also was our idea. Yeah.
Okay, and in the discussion, it turned out, which wasn't mentioned at the beginning, that the fact that sand is a wettable material is extremely important in the formation of the crater. So you said that trapping of the sand in the water increases viscosity. I would also suspect that it increases the mass of the droplet. And I was wondering which effect is more important.
Absolutely. There's a great question, I think. So to answer this, well, what I found in literature was more about talking of the viscosity of the water, but it's true that the mass, we should compare the inertia of the wet sand with the viscosity of the wet sand. We didn't do this, but we could compare viscosity versus inertia, probably, to answer the question.
And my last question, have you performed experimental verification of the accuracy of your solution to the inverse problem? Like comparing how statistically accurate you are in determining the parameters.
So we tried several times the inverse problem. We didn't have a statistical really answer, but what we can say is the uncertainty we computed is quite precise, around 10 to 20%.
I continue answer a question that was established before. I am wondering how can you say that you can predict the speed of the drop?
Yes.
Without characterization of the sand.
How we can predict? Okay, so what we found in literature, what we tested with two types of sands, is that the law which we have, which relates the Weber number to the size of the maximal size of the crater, does not really depend on the type of sand, for example. If it's compact, it depends a little bit more, absolutely. The compactness is the more relevant parameter here. But if we have a normal sand, so not compacted, but if you just place it normally, it's not very it's significant. And what we see here, I think I have the curve just a little bit after, is that, yeah, it doesn't depend really on the size, and it doesn't. We tested with two types of sands which were quite different, and we found the same type of exponents.
It's interesting. I don't know though, where is the separation between compact and not compact sand.
There is a coefficient phi. I think it's about 0.70, where you really see a critical difference in the behavior.
Very quick experimental question. A lot of the parameters here depend on the temperature. You said you didn't vary the temperature, but did you make sure it was constant? Was there some sort of temperature control?
So we only tried with hot water once, and then we didn't vary it. No, we're in the room temperature. So to be honest, no, but it was
okay.
Plus minus 5 degrees, I think.
So I have a question about this tilt, because in the theory you neglected the gravity. So it means that there's no really actual axis, which is the main one. So it shouldn't really matter if you tilt the surface or if you add the horizontal velocity. Is it right?
No, yeah, the velocity is horizontal, but the surface can be inclined.
Sorry, that velocity. So basically...
Yes, we only looked for vertical velocities, but the inclination angle was for the plane of the sand. I wasn't clear about that, maybe. So we inclined the plane of a layer of sand.
Yeah, I know. So will you expect the same results if you now add some horizontal velocity so that the impact angle would be the same as it is just tilted? Do you know what I mean? Or
I
should
see. I think I see what you mean. Well, so if we take a tilted plane, almost vertical limit case, we expect the impact size being much bigger. And if we have an impact speed, it should be bigger also, but less probably, I'd say. Because with limiting case reasoning, you get that the impact will be not as big as expected.
Okay, thanks.
May I? Okay, so I might just have missed this in the discussion, but what are the exact requirements for rebounds?
So high speed, so high enough energy for rebounds, and maybe a hydrophobic surface really helps.
Okay, and you've gotten every question so far, so do the opponent and reviewer agree, or would you like to add anything in terms of requirements for the rebound side?
Actually, there is video on YouTube that you can see that it is splash and go up, and of course hydrophobic helps to be it, and as we have seen through solution, it cannot be absorbed for the dry sun because it's absorbed, like not the sun, but the water absorbs sun and becomes too heavy to bounce back, so it should be not so much sand in the water to be bounced back, and of course viscosity plays a role. And surface tension, it should be like bigger than the force from inertia that tries to drag it. And for certain parameters, it could be achieved and absorbed even. And it would be maybe further improvement to see for parameters, look for parameters that can be achieved in such system.
I think the requirements are high velocity and the hydrophobic surface too, but the both of two, because maybe if the velocity is not too high, the droplet just can be deposited on the surface.
Okay, thank you.
So I'd like the reviewer give a chance to speak. In your presentation, you suggested that the parameter space to study is enlarged by humidity, packing factor, and thickness of the layer of sand. And this was after Mattia explained that they reduced the dimensionality of the parameter space because it would be extremely difficult to handle if there were many parameters. So I would like your opinion about why these factors are somehow equally or more important than those that were studied?
I think they are not so equally. I think the parameters of the sand are important. Changing the packing fraction is very difficult, but changing the thickness of the layer of sand is easier to do. And I think it can affect how much the surface under the layer can deforms and cause perturbations on the crater formation.
I don't know, I'm a bit afraid to ask a daft question to tell me if it is daft, but I was quite interested in studying your study in the tilt the plane of the sand. But if I go to a beach, you know, and sometimes you see a lot of a very varied topography in the sand. So what happens if you have a V-shaped surface in the sand? Then hopefully, have you thought to study that? Because at the moment, all I feel like I've seen is if you look at a flat surface.
Yeah, I think that's a very interesting question. So we took a constant angle, then we can apply this maybe to a V-shape in a linear approximation. Now, if the size of the V-shape is very small compared to the size of the drop, then it wouldn't apply in that case. We would have to do another type of study. But what is sure is that if the angle is higher, then the impact size is higher.
Okay, that's good. Thank you.
Okay, I think we have finished with the jury questions. Thank you very much. So I'll give stay there on the stage. And so yeah, I will give the juries a minute to decide their marks. Their last marks. Oh my God.
Go here, for example.
Yeah.
Everybody cheese.
Beautiful.
Hey.
Thanks.
Yeah. Are we ready?
Oh, great. Tactical rejection. No, they want to deliver the remark section.
Okay, I think that we are ready. So last but not least, the comments from our jury members. So who wants?
Thank you. I like the report. It was pretty nice, despite actually, I would say you studied the influence of hydrodynamic side of it and overlooked the granular physics dynamic, whatever is there, perspective, and liked it. But the cool story is that you actually managed to make some hypotheses and prove them and validate them. It was done pretty well. I would make a very surprising comment. I don't believe I'm saying it now. We usually like complaining as jurors that the reviewer took a role of a second opponent on the stage, and we put grades because of this reason. In this fight, I would say the opponent took some bit of reviewer role, because you tried to. Maybe it wasn't intentional. I don't know what you had in your mind, but from my perspective, it looks that you tried to put a reviewer somehow aside and moderate discussion yourself and introduce new points for discussion by your own, rather to letting reviewer doing it. I cannot validate whose points were of higher priority or which are very important, but the classical approach is that the reviewer does it. It's my comment on from the game side. Thank you.
It's interesting pointed out, because I didn't actually catch that, but now you say it. I'm like, oh, that's right. I thought it was a really good discussion. It was a really good problem, and all the questions they had to you, you're like, whoo, and just answered it. And I thought that was phenomenal. What I missed a little bit in the discussion was some more theory, I guess, or it was a very qualitative. It was a lot of clarifying questions, essentially, rather than going into the physics more in depth. But overall, I thought it was a really nice fight, and for me, you all scored pretty high. So congratulations.
I agree with Susanne about the scores. Maybe I kind of high, mine as well. Why? Because this round for me was the best of the three, because you had a lot of work. So you managed to discuss a lot of stuff. You went to a lot of details about this case. Usually in these fights, in the discussion, they say, "Oh, you could study that." And it then like, oh yes, we could do that, but you actually did. You did prove that the resistance was negligible, and you have a lot of images about the drops, and also you have a theoretical model. And for me, it was a good fight. Both there was this issue about the opponent and reviewer, but when I thought about that, I thought like that it was not that the opponent was taking the role of the reviewer, but more like the fight was reporter and opponent and God, something like that. And that's it. Like I was very pleased.
Yeah, building upon a few of the previous points. So this problem's amazing because it has such a huge parameter space, and there's so much you can do, and you've only got, in this case, 12 minutes to present, and just up to 9-10 minutes of discussion time. So I kind of want to start with feedback to the opponent is, and as an experimentalist, I love to see this large parameter space. So you had 2 pages of discussion points, which is, amazing. I can't wait to dig into that. But the thing is like even in research, we have limited time and, a limited story space in our book to write. And I wonder, when I look at this problem brief, I look at, especially in particular the inverse problem, I want to know what parameters can help me optimize or go to the limits of this inverse problem. So I'm wondering if, as the opponent, especially when it comes to proposing a discussion, is focus on some of fewer points to discuss, which helps me optimize the solution for this inverse problem. And of course, this goes on to the report. I think it's an amazing overall well done job, and I think despite, of course, the current literature around it, you've tried to work pretty hard to expand on the novelty of it. So well done. Just finally with the reviewer role, I think overall very good. Maybe a bit, again, it always depends on the personalities on stage, but in some cases a bit too timid to take hold of that, take back control of that role. But again, it's always a bit of a very difficult thing depending on who's on stage. But still, well done. Thank you.
What I'm not too complained about right now, I loved. So first, the presentation. For most of the presentation, I felt like we were going to Pisa to climb the tower and to throw stones on the passers-by, the Galileo method. And only towards the end of presentation, what was shown was not repeating the results which were obtained earlier in the literature, and there were some own ideas and hypotheses. And I really didn't like that this wasn't stressed. So this is my comment for the presentation. So I have to say that I very much liked the very active role of the opponent, and I have to say that your aggressive, a little bit activity prompted the reporter to reveal so much more about the report. So, but I think that what happened and what sent shivers down my spine was the moment that you asked about the paper about the asteroids, because there was a chance that Mattia wouldn't know it, and he did. So I didn't like it. And for the reviewer, I have to say that this was a very difficult situation because we had a lively discussion going on the stage, which could exactly do without you. And you understood it. I'm like, your grade is the highest of all the 3 I gave. And the only thing that I didn't like is that you succumbed to the temptation from your team to take the mic and to ask some questions that diverted the topic of the discussion. So I mean, like, I just very much like that you knew where to when to withhold your activity.
Okay. Uh, I don't have spoken to know the different facts. I want to maybe make a general remake. I think it was very nice for me. As you say, this is we learn a lot. I think it's the most important point here. And I want to say that for our country, I'm from Colombia, it's very important to that's happening here. And I am very proud of that. And I think it's a big effort also for you is to stay here. But I think it was, have seen that to know is very nice. Fight, it's an idea fight to share your knowledge, to try to defend your ideas, try to push another to get the better. This is very beautiful. I think the discussion here was very nice. You pushed him to show something that this was not presented before, but I think you show that allows you to present everything. This was important. I think something important, differently to you, is that the presenter has to know what is the main point and left something behind that this could be asked, and you do it. I think it was very nice, and you also appoint this point as the good to take the overview of the problem. This was very nice, and for you, it's difficult, as you say, no? The fight is so too interesting that you, what can I say? I don't know. That's okay. Thank you very much.
Yes, I'll be quick, yeah? So to the reporter, I really like your presentation. I see what you did there, right? So yeah, I have to commend you on your bravery to choose this problem because it's very complex. The parameter space is huge, and you could know in forward that the opponent could raise like a million questions, which he did, and this is good, right? And I think he managed to find the one parameter you didn't get to study. So yeah, this led to a lively discussion, and I agree with everyone that the reviewer had the toughest job here because the discussion was already very fruitful, and also I think that yeah, the opponent overtook the role a bit, but it didn't really influence the dynamic of the talk too much. Yeah.
Okay, we have finally finished the final of the 14th edition of the IPT 2022. Woo! Big round of applause! So I want you to give incredible congratulations, a round of applause for each one of the 3 teams that made it to the final, because this was an incredible final to see, no matter in which position you end up. So yeah, thank you very much for giving us this incredible final, and now we get to the lunch. So we have to fix this salon for the lunch, with the tables and everything, so need some help with the chairs. And okay, yeah. Great.